There are structures in the universe so vast, they stretch across millions of light years, so immense, they dwarf entire galaxy clusters, yet we cannot see them with our eyes. These are not glowing stars, not swirling galaxies, not fiery supernovae. They are ghosts in the radio sky. Silent in optical light, but roaring in radio waves. These cosmic leviathans reach out into intergalactic space like invisible tendrils of power, carrying the voice of ancient black holes across the void. They are called giant radio galaxies, and they might just be the largest single galactic structures in the known universe, only visible when we learn to listen instead of look. But before we continue, subscribe to the channel so you don't miss out on any of these videos. A giant radio galaxy, often abbreviated as GRG, is not a typical galaxy. It's an astronomical structure composed of a central host galaxy and two enormous lobes of radio-emitting plasma, often extending millions of light years in opposite directions. These lobes aren't made of stars or planets. Instead, they're inflated by jets of relativistic particles, fired like cosmic cannons from the galaxy's central supermassive black hole. While regular galaxies like our Milky Way are around 100,000 light-years wide, GRGs can exceed that by a factor of 10, 100, or even more. To qualify as a GRG, a galaxy's radio structure must span at least 0.7 megaparsecs, which is over 2 million light-years. But some giants go far beyond that. Incredibly, we've now found GRGs that stretch more than 16 million light-years across. That's more than 150 times the size of our entire galaxy. Here's the catch: you can't see them in normal telescopes. If you pointed an optical telescope at a GRG, you'd see just a faint elliptical core, a quiet-looking galaxy, nothing dramatic. But if you observe it in radio frequencies, the true form is revealed. Massive twin lobes emerge from either side of the galaxy, connected by narrow jets, painting a structure so colossal it takes your breath away. These radio lobes are created by jets of charged particles, mostly electrons, traveling near the speed of light. They are launched from the poles of the central supermassive black hole, energized by the twisted magnetic fields and spinning accretion disk that surrounds it. As these particles spiral through magnetic fields, they emit synchrotron radiation, a type of radio wave emission that allows us to detect the jets and lobes even long after the black hole stops feeding. What's astonishing is how well structured these GRGs are. Despite their vast size, the two lobes are often highly symmetrical, suggesting incredibly stable black hole activity for tens or even hundreds of millions of years. This symmetry, two jets beaming in nearly perfect opposition, shows that these are not random structures. They are the long-term result of sustained, directed energy flow on scales that defy ordinary human comprehension. And yet, they remain strangely hidden from us. Not because they're rare, though they might be, but because they're largely invisible in the light we're used to. It's only through radio astronomy that we began to detect them, realizing that these ghostly behemoths exist in far greater numbers than we thought. Many may have been catalogued as ordinary galaxies, with their gigantic lobes missed entirely simply because we weren't looking at the right wavelengths. Most GRGs are found in giant elliptical galaxies, often the result of galactic mergers. These mergers can feed the central black hole with fresh material, triggering a burst of activity and launching new jets into space. Over millions of years, those jets inflate the lobes farther and farther, sculpting the vast structure of a GRG. In this way, giant radio galaxies are time machines. They carry within them the fossil record of past black hole eruptions. The jets reveal how powerful and stable the central engine once was. The lobes trace how far that energy has traveled. Some show evidence of restarting, of multiple epochs of activity, suggesting that the galactic nucleus can go dormant and reignite, again and again, over cosmic timescales. So what are giant radio galaxies? They are the universe's loudest whispers, colossal messengers from the hearts of galaxies, whose stories are written not in light, but in radiation. They are galaxies, yes, but galaxies that have broken the mold. Galaxies with wings. Galaxies with reach. Galaxies whose true form is so vast, it spills far beyond their stars, revealing a hidden universe of unimaginable scale. For most of human history, we explored the universe with only our eyes. Even with the invention of the telescope, our cosmic window remained narrow, bound to the sliver of the electromagnetic spectrum known as visible light. The stars shimmered, nebulae glowed, and galaxies turned gently across the sky. But what we were seeing was only a fraction of reality. The universe, as it turns out, is broadcasting a far richer and stranger message, one that is not seen, but heard. That revelation began in the early 1930s, almost by accident. A young engineer named Karl Jansky, working at Bell Telephone Laboratories, was trying to find sources of interference that might disrupt transatlantic radio communication. Using a massive rotating antenna, he picked up a curious, persistent hiss. At first, he suspected it came from thunderstorms. But then he noticed the hiss returned every day, slightly earlier each time. Eventually, he realized that the signal was following sidereal time, not solar time. The source wasn't on Earth. It was coming from the center of the Milky Way. With that accidental discovery, radio astronomy was born. And with it came a revelation: the universe was far louder than we had ever imagined. In the decades that followed, radio astronomers began to map the sky using enormous radio dishes instead of optical lenses. What they found was astonishing. Many seemingly ordinary patches of empty sky, completely dark in visible light, were brimming with powerful radio emissions. These signals didn't come from stars. They came from something far more energetic: active galactic nuclei, quasars, pulsars, supernova remnants, and most notably, galaxies whose radio emissions extended far beyond the visible boundaries of their stars. Among the most mind-bending discoveries were strange double-lobed shapes that appeared in radio maps. These weren't artifacts. They were real structures, each connected to a tiny central point source. At first, astronomers didn't know what to make of them. But as data improved, it became clear: the central point was a galaxy, and the lobes, stretching millions of light years, were enormous outflows of radio-emitting plasma. It was as if someone had taken an ordinary galaxy and given it invisible wings. This was our first glimpse into the hidden population of giant radio galaxies, vast, sprawling structures whose existence had gone completely unnoticed until we tuned into their frequencies. The night sky, once thought to be mapped and catalogued in visible light, was suddenly transformed. Where we had seen isolation, there was structure. Where we had assumed silence, there was roar. Radio astronomy didn't just uncover giants, it rewrote the cosmic hierarchy. It revealed that the most energetic events in the universe weren't explosions of light, but outbursts of relativistic particles. It showed us that black holes could launch jets across cosmic distances. It introduced us to lobes so large, they could engulf entire clusters of galaxies. Even the classification of objects had to change. Galaxies were no longer just galaxies. They could be radio galaxies, quasars, or blazars, depending on the nature of their emissions and orientation. And among them, the giants, those stretching over 2 million light-years, formed a class of their own. These weren't anomalies. They were part of a hidden structure that only became visible once we stopped looking and started listening. Modern radio telescopes like the Very Large Array, VLA, the Low Frequency Array, LOFAR, and MeerKAT have continued this legacy, mapping the radio sky in unprecedented detail. What they've found suggests that the universe is filled with old, faded, and often fossilized radio giants, remnants of past black hole activity, floating invisibly in space until illuminated by radio waves. And as radio astronomy pushes to even lower frequencies and higher sensitivities, we're starting to see even fainter and more distant GRGs, galaxies that may have turned off their central engines long ago, but still carry the echoes of their titanic outbursts. Through radio, we've discovered that the cosmos is far more dynamic than we once believed. Black holes don't just consume, they create. Galaxies don't end at their stars. They extend far into the dark with structures invisible to our eyes. And the night sky is not a silent stage, but a humming, whispering sea of energy, stretching from one end of the universe to the other. The radio universe isn't just an alternate view, it is the true scale of the cosmic drama, and giant radio galaxies are among its loudest and oldest performers. At a glance, a giant radio galaxy might not seem extraordinary. If you observed one through an optical telescope, you might see a simple elliptical galaxy, a smooth, featureless ball of ancient stars, perhaps slightly larger than average, perhaps not. There might not be any spiral arms, star-forming regions, or dramatic gas clouds. It might even appear faint, dimly glowing amid the darkness of space. But that's only what your eyes allow you to see. The truth, as revealed by radio telescopes, is that a GRG is nothing like a typical galaxy. It's a radically different kind of cosmic entity, one whose most significant features lie far outside the boundaries of its stars. Let's begin with size. The Milky Way, our home galaxy, spans about 100,000 light-years. Even the largest known spiral galaxies top out at a few 100,000 light-years. But GRGs are in an entirely different league. Their defining feature is the colossal length of their radio lobes, twin structures launched by the galaxy's central supermassive black hole, stretching in opposite directions across intergalactic space. To be classified as a GRG, those lobes must extend at least 2 million light-years from end to end. And many are far larger. Some, like Alcyoneus or 3C236, span over 10 million light-years, with the record holders reaching past 16 million. That's more than 150 times the diameter of the Milky Way. These aren't just distances. They represent structured, energetic, and highly ordered regions of plasma, shaped and maintained by the galaxy's central black hole over tens or hundreds of millions of years. By comparison, most galaxies, even the active ones, rarely produce jets or lobes that exceed a few 100,000 light-years. GRGs are extreme outliers, the titans of their class. But it's not just size that sets them apart, it's structure. Typical galaxies, whether spiral or elliptical, are primarily composed of stars, gas, and dark matter bound into a single, gravitationally cohesive body. A GRG, however, consists of a compact stellar core and then two vast, external components, the lobes, that are not made of stars at all. These lobes exist outside the visible galaxy, beyond its halo, beyond its gas disk, beyond even its dark matter envelope. They are independent structures, inflated and energized by particle jets that pierce through the surrounding intergalactic medium. The power source is another difference. While most galaxies have central black holes, they are usually dormant. In a GRG, the black hole is, or was, active, accreting gas and ejecting energy at near light speeds. The black hole becomes an active galactic nucleus, AGN, launching twin jets that shoot far beyond the galaxy's stellar component. These jets then terminate in hotspots, regions where the outflow slams into surrounding material, and inflate the lobes like twin cosmic balloons. In typical galaxies, this process either doesn't occur or is far more limited in scope and power. The magnetic and relativistic nature of GRGs is also unique. Their lobes glow via synchrotron radiation, light emitted by electrons spiraling around magnetic field lines at relativistic speeds. This kind of emission is rare in ordinary galaxies but dominates the energy profile of GRGs. In fact, the lobes can contain more energy than all the stars in the host galaxy combined, distributed over volumes many thousands of times larger than the visible galaxy itself. There's also the element of age and history. GRGs aren't born overnight. They evolve over hundreds of millions of years, requiring sustained black hole activity to keep the jets flowing and the lobes expanding. Many show signs of multiple phases of activity, periods where the jets turned on, turned off, and then restarted. This episodic behavior leaves behind relic lobes, double-lobe structures, or faint fossil trails. A typical galaxy has a quieter life cycle, evolving through star formation and gravitational interactions, but rarely producing such enormous, enduring traces of its central black hole's fury. The environment plays a role too. GRGs tend to live in low-density regions of space, cosmic voids or sparse outskirts of galaxy groups, where their jets and lobes aren't quickly disrupted by surrounding matter. In contrast, typical galaxies may sit in dense clusters, where radio jets are confined or bent by nearby galaxies or the intracluster medium. The very location of a GRG is often what allows it to grow unchecked into a truly giant. In a way, GRGs reveal a hidden dimension of galactic identity. They show us that a galaxy isn't just its stars or gas, or even its dark matter halo. A galaxy can also be defined by its invisible voice, its ability to shape the surrounding universe through sheer force of energy. GRGs speak in radio, not light. They grow not by forming stars, but by pushing plasma. And they live not just as starry islands, but as engines of intergalactic influence. So when we compare GRGs to regular galaxies, the contrast is almost poetic. One is quiet, luminous, and self-contained. The other is explosive, invisible, and unbound. One lives within its own light. The other stretches far beyond its body, announcing itself across the cosmos in waves we can't even see. They are galaxies, but they are not typical. They are monuments of momentum, trails of lightless fire, the grandest footprints of black holes gone wild. When radio astronomers began peeling back the layers of the invisible universe, they didn't just find a few strange anomalies, they uncovered giants. And among these giants, some names now stand out like legends written across the radio sky. These aren't galaxies as we once imagined them. They're titans, massive, ancient, sprawling structures that defy the boundaries of imagination. Let's meet some of the most famous among them: Alcyoneus, J1420, 0545, and 3C236. Alcyoneus is, quite simply, the largest known giant radio galaxy ever discovered. Found by astronomers using data from the LOFAR radio telescope, a low-frequency observatory scanning the skies for faint radio emissions, Alcyoneus was hiding in plain sight for years. Its central host galaxy is unremarkable in optical light. There's nothing flashy about it. It's a quiet elliptical galaxy sitting over 3.5 billion light-years away from Earth. But when viewed in low-frequency radio wavelengths, its true scale is revealed. From one end of its radial lobes to the other, Alcyoneus stretches more than 16 million light-years across. That's not just big, it's colossally unprecedented. For comparison, our Milky Way is 100,000 light-years across. Alcyoneus is 160 times that size. Its lobes are so large, they would engulf entire clusters of galaxies. And yet, its radio emission is incredibly faint, so faint, in fact, that it was missed for decades until newer, more sensitive radio maps were constructed. Its discovery proved a key point. We may be surrounded by more of these giants, hidden just beneath our current technological threshold. What makes Alcyoneus even more fascinating is how ordinary its host galaxy appears. It's not the most massive. Its black hole doesn't seem exceptionally large. And yet, it has produced the longest radio structure we've ever seen. That raises deep questions. Is Alcyoneus an anomaly? Or are there more like it, quiet monsters, whose environments allow them to stretch so far without interference? Then there's J1420, 0545, another contender for galactic enormity. It once held the record as the largest known radio galaxy, spanning around 15 million light-years. Its structure is nearly textbook perfect, symmetrical twin lobes extending from a compact central host. J1420, 0545 is especially notable for the narrowness of its jets, which remain tightly collimated even after millions of light-years of travel. That kind of stability suggests an unusually quiet intergalactic environment, allowing the jets to propagate with minimal disruption. But perhaps more intriguing than its size is its youth, relative to its size, of course. The jets in J1420, 0545 appear to be relatively young in cosmic terms. That implies the galaxy's central black hole must have been extremely efficient at launching powerful outflows over a short timescale, allowing the lobes to grow rapidly. In this case, the galaxy is not just a giant, it's a fast-growing one. And again, its host galaxy is modest. Nothing in its optical appearance would prepare you for the behemoth hidden in radio waves. And then we come to 3C236, one of the earliest identified and still one of the most studied giant radio galaxies ever discovered. Unlike Alcyoneus and J1420, 0545, 3C236 has been on our radar, quite literally, for decades. Located around 1.1 billion light-years away, it spans over 15 million light-years, making it one of the largest known radio galaxies as well. But 3C236 brings something new to the table: complexity. Its radio structure reveals signs of multiple episodes of jet activity. It doesn't just have a pair of lobes, it has layers. Some of these lobes are faint and diffuse, indicating past activity that has since faded. Others are sharper and brighter, suggesting recent jet reactivation. In essence, 3C236 is a galactic palimpsest, preserving multiple histories of black hole eruptions over cosmic time. It shows us that some giant radio galaxies aren't built in a single, uninterrupted outburst. Instead, they may turn on, switch off, and restart, leaving behind overlapping signatures from different epochs. Adding to its mystique, 3C236 has a dusty disk of gas and evidence of ongoing star formation, somewhat unusual for massive ellipticals hosting large radio lobes. This raises the possibility that interactions or mergers could be feeding the central black hole, fueling fresh jet activity every few 100 million years. Together, Alcyoneus, J1420, 0545, and 3C236 form a kind of holy trinity of radio giants, each representing a different aspect of what a GRG can be. One is the quietest and biggest, the second is the youngest and fastest growing, and the third is the most complex, with multiple lifetimes encoded in its structure. These galaxies are not just anomalies, they're windows into extreme physics. They challenge our understanding of black hole behavior, intergalactic environments, and the limits of energy transport in the universe. They suggest that galaxies are not bounded entities, but rather dynamic engines, capable of shaping the cosmos far beyond their visible borders. And they hint at a deeper truth, that we have barely scratched the surface. For every Alcyoneus we find, there may be 10 more, fainter and farther, whispering through the cosmos in radio silence, waiting for our ears to finally be sensitive enough to hear them. Alcyoneus is not just a galaxy, it is a monument to scale, silence, and the persistence of cosmic energy. When astronomers discovered it in early 2022, it redefined the known limits of how large a single galaxy-related structure could be. Not because it burned brightly, not because it stood out in optical surveys, but because it remained completely hidden, stretching quietly across 16.3 million light-years, whispering through the void in the lowest frequencies of radio light. Its name, inspired by the mythological giant Alcyoneus from Greek mythology, is well-earned. In myth, Alcyoneus was said to be unconquerable so long as he fought in his native land. In astronomy, the galaxy named after him seemed almost equally elusive, concealed within the depths of the LOFAR 2-meter sky survey, LOTSS, a massive project that scanned the northern sky in ultra-low radio frequencies using the LOFAR array. The discovery came not through chance, but through careful, deep data processing. Alcyoneus had been passed over in previous surveys simply because its emission was too faint, too diffuse, and too extended for older instruments to detect. It wasn't bright or flashy like other well-known radio galaxies. It didn't scream. It murmured, and LOFAR, with its unprecedented sensitivity to low frequencies and wide angular resolution, was finally quiet enough to hear it. The galaxy's host is surprisingly modest. It's a relatively normal elliptical galaxy located about 3.5 billion light-years away, with a central supermassive black hole that doesn't appear particularly massive or hyperactive. That alone made astronomers pause. Alcyoneus, the largest known giant radio galaxy in existence, wasn't hosted by a cosmic juggernaut. It wasn't anchored by a quasar or surrounded by dense clusters of galaxies. It was ordinary. And that made it extraordinary. How does a seemingly typical galaxy produce the longest known radio lobes in the universe? That question strikes at the heart of GRG formation. One clue lies in environment. Alcyoneus appears to live in a low-density region of the universe, possibly on the edge of a cosmic void. That lack of surrounding material means there's very little to stop or slow the outward expansion of its jets and lobes. Like smoke expanding into a vacuum, the radio structures could drift and grow with little resistance, perhaps for hundreds of millions of years. But longevity alone doesn't explain its enormous span. The jets from the central black hole must have remained stable, coherent, and relativistic for an incredible amount of time, likely over 1 billion years. That implies a sustained phase of active galactic nucleus, AGN, activity, which is relatively rare. Most galaxies go through shorter bursts of AGN behavior, followed by long dormant periods. Alcyoneus may have been feeding steadily and quietly for eons. Its lobes, when viewed in radio images, are ghostly, faint, filamentary structures ballooning outward from the core, connected by thread-thin jets. These lobes don't burn with high brightness like in younger, more powerful radio galaxies. Instead, they glow softly, likely due to aged synchrotron electrons, whose energies have slowly degraded over time. In fact, the lobes are so faint that they may be nearing the end of their visibility, making the discovery especially fortunate. We may have caught Alcyoneus at a cosmic twilight, still glowing, but fading. And yet, what we see today is only the afterimage of past violence. The electrons that make up the lobes must have traveled for millions of years, propelled by jets that launch near the speed of light. Over those vast distances, they trace the contours of invisible magnetic fields, forming the filaments and arcs we observe. All of this, orchestrated by a supermassive black hole in a galaxy that, in visible light, looks no more remarkable than thousands of others. Alcyoneus is also reshaping how astronomers search for other GRGs. It suggests that we've likely underestimated the population of such giants. If the largest known radio galaxy could remain undetected until now, how many more lie hidden, too faint, too extended, or too distant for our instruments to notice? Alcyoneus might be a record holder, yes, but it may also be the tip of the iceberg. Beyond its staggering size, what Alcyoneus truly represents is a shift in our understanding of galactic potential. It shows that you don't need an ultra-powerful black hole, or a chaotic environment, or extreme feeding events to grow a giant. Sometimes, all it takes is time, persistence, and a quiet corner of the cosmos. As we continue to improve our radio surveys with next-generation instruments like the Square Kilometre Array, SKA, the legacy of Alcyoneus will be foundational. It's the benchmark, the quiet colossus that challenges everything we thought we knew about what a galaxy can become when left undisturbed for cosmic eons. Its lobes now stretch across a space larger than any single galactic structure ever discovered, unfolding like a cosmic breath, silent but powerful, across 16 million light-years of time and space. When we say that a giant radio galaxy like Alcyoneus spans 16 million light-years, the number itself can feel almost meaningless, too vast to visualize, too abstract to grasp. It's like saying the ocean is deep or the universe is old. But to truly appreciate the scale of these titans, we need to anchor them to things we do understand. We need to compare them to cosmic structures we're already familiar with, to place these invisible colossi into context. So, let's break it down and ask the question, how big is that, really? Let's begin with our home, the Milky Way galaxy. It's an impressive spiral galaxy, roughly 100,000 light-years in diameter. When you look up into the night sky and see the broad stripe of the Milky Way overhead, you're glimpsing just a fraction of its stellar disk, home to hundreds of billions of stars, countless planetary systems, dust lanes, nebulae, and more. From our perspective on Earth, the Milky Way already feels enormous. It takes light over 100,000 years to cross from one end to the other, and yet in the realm of radio giants, it barely registers. A typical GRG, even on the smaller side, is over 2 million light-years across. That's already 20 times wider than our galaxy. Alcyoneus, stretching across 16.3 million light-years, is a staggering 163 times the diameter of the Milky Way. Think about that. If the Milky Way were the size of a coin, Alcyoneus would be the size of a dining room table. If you place the Milky Way at the center of Alcyoneus's radio lobes, those lobes would extend well beyond not just the edge of our galaxy, but beyond the orbits of neighboring galaxies. To help visualize it, let's scale things down. Imagine the Milky Way as a 10-inch dinner plate. A typical GRG would be a circle 16 feet wide. Alcyoneus? You'd need a football field to represent its full extent. And that's just in terms of width. We're not even talking about volume, or the actual space filled by its lobes, which are not thin lines but balloon-like structures extending into the third dimension, vast clouds of relativistic particles that occupy space more like cosmic continents than filaments. Now consider the local group, the collection of galaxies to which the Milky Way belongs. The local group includes Andromeda, Triangulum, and about 50 smaller satellite galaxies, and it spans about 10 million light-years across. That sounds significant, until you realize that Alcyoneus is over 1.5 times larger than the entire local group. That's right. This single radio galaxy's extended lobes stretch farther than the distance between our galaxy and the Andromeda galaxy, our nearest large galactic neighbor. If Alcyoneus were centered on the Milky Way, one of its lobes would extend past Andromeda, and the other would reach far beyond the outskirts of the local group into true intergroup space. We can also compare GRGs to galaxy clusters, which are among the largest gravitationally bound structures in the universe. A typical galaxy cluster, like the Virgo cluster, contains hundreds or thousands of galaxies and spans 10 to 15 million light-years. These clusters are colossal in mass and content, bound together by gravity and suffused with hot intracluster gas that shines in X-rays. Alcyoneus is on the scale of such a cluster, but it's not a cluster. It's not composed of hundreds of galaxies. It's the footprint of a single galaxy, a solitary elliptical with a black hole that managed to inject energy so far into space that it now competes in size with entire clusters. This comparison changes how we think about structure. A GRG is not a dense ball of galaxies packed into a cluster. Instead, it's more like a cosmic octopus, with tendrils, its radio lobes, extending into intergalactic space, loosely shaped and gently expanding for hundreds of millions of years. These lobes may not have the mass of a galaxy cluster, but in terms of their spatial scale, they are comparable, and often larger. Let's zoom out even further. The largest superclusters, like the Laniakea supercluster, which contains the local group, span around 500 million light-years. That's much larger than any GRG, of course, but the difference here is scale of source. Superclusters are collections of clusters and groups, vast tapestries of structure. But Alcyoneus is a single galaxy's outflow. Imagine one tiny node in a supercluster launching tendrils that reach across its section of the cosmic web. That's what we're seeing. One black hole, in one galaxy, painting its history across a chunk of the universe tens of millions of light-years wide. Even cosmic filaments, the vast bridges of gas and galaxies that form the backbone of the cosmic web, can be compared to GRGs. Some filaments are hundreds of millions of light-years long, but their thickness is often measured in tens of millions of light-years. Alcyoneus's lobes can thread between these filaments, weaving into the large-scale structure in ways we're only beginning to understand. So let's revisit that number, 16.3 million light-years. Light itself, the fastest thing in the universe, would take over 16 million years to travel from one end of Alcyoneus to the other. That's longer than it took humans to evolve from our earliest ancestors. When the light we now detect from one end of Alcyoneus's lobes began its journey, Earth was in the midst of the Miocene epoch. Mammoths had not yet appeared. The Himalayas were still rising. The Atlantic Ocean was narrower. In every possible way, GRGs stretch not only through space but through time. Their lobes record millions of years of energy flow. They grow as the universe evolves around them. They are, quite literally, fossils in motion, tracing the motion of particles through distances and times that boggle the mind. It's worth imagining what would happen if such a structure existed near us. If a galaxy like Alcyoneus were centered on the Milky Way, its lobes would span far beyond our nearest neighbors, encompassing dozens of galaxies, possibly shaping the intergalactic medium between them. The Earth would be embedded within one of those lobes. And yet, unless we had radio telescopes tuned to the right frequencies, we'd never know it was there. We'd drift silently within a ghost, unaware of its presence, unable to see the plasma ocean flowing above and below. This is why radio astronomy has become so vital. Without it, structures like GRGs remain invisible, enormous, elegant features of the universe that leave no mark in optical light. And as our tools grow more sensitive, we begin to uncover more of them, not just the giants, but the faded remnants, the reignited relics, the fossil lobes stretching across space like the ancient breath of cosmic winds. We live in a universe where a single galaxy can influence space across a scale that once seemed impossible. Where matter launched from a black hole can travel millions of light years and still carry the signature of its origin. Where size, age, and energy intertwine into the graceful forms of twin lobes echoing through the void. Alcyoneus, and giants like it, redefine our idea of a galaxy. They are not just collections of stars. They are engines of motion. They are storytellers of ancient activity. They are the sculptors of space. And in terms of size, there may be no greater expression of that truth. In the realm of giant radio galaxies, vision is not enough. You could gaze at the sky with the world's most powerful optical telescope and still miss some of the largest structures the universe has ever produced. That's because these cosmic leviathans don't shine in visible light, they speak in radio. Their twin lobes, stretching millions of light years, emit a type of radiation called synchrotron emission, generated by relativistic electrons spiraling through magnetic fields. And to detect that signal, we need an entirely different kind of eye. Enter the radio telescope, an instrument not built for seeing, but for listening. Unlike traditional telescopes that gather photons in the visible spectrum, radio telescopes are tuned to much longer wavelengths. They're designed to detect the subtle, often faint hum of the universe's deepest frequencies. And it's through these instruments that we've begun to peel back the darkness and reveal a hidden universe, one where galaxies erupt with energy, jets stream across the cosmos, and lobes balloon into invisible wings. Among the most important tools in this revolution is LOFAR, the low-frequency array. LOFAR isn't a single dish, but a vast network of radio antennas spread across Europe, with its core in the Netherlands. Unlike the towering dishes we often associate with radio astronomy, LOFAR stations look more like alien meadows, flat fields of simple antennas, each one receiving faint signals from space. LOFAR specializes in low-frequency radio waves, typically between 10 and 240 MHz, which makes it perfect for detecting the aged, diffuse emissions of GRGs. Many of the largest known giants, including Alcyoneus, were only visible thanks to LOFAR's unprecedented sensitivity to these deep, low-frequency signals. What sets LOFAR apart is its interferometric power. Each station records data simultaneously, and these signals are then combined computationally to act as a virtual telescope with a resolution determined by the distance between the farthest stations, known as the baseline. This effectively gives LOFAR the angular resolution of a telescope hundreds of kilometers wide. That level of detail is crucial when identifying faint, extended structures that might otherwise blend into background noise. But LOFAR isn't alone. It's part of a larger movement in radio astronomy that includes titans like the Very Large Array, or VLA, in New Mexico, USA. The VLA is one of the most iconic and versatile radio telescopes on Earth. Composed of 27 movable dishes, each 25 meters wide, the VLA can rearrange itself into different configurations depending on what astronomers need: tight clusters for stronger signals or wide spacing for higher resolution. The dishes work together through interferometry, just like LOFAR, creating an image far sharper than any single dish could manage. The VLA has played a foundational role in mapping radio galaxies for decades. It was through the VLA that many classic radio galaxies, like Cygnus A and 3C236, were first mapped in detail. Its ability to resolve fine structure in jets and lobes helped scientists understand the physics of jet collimation, hotspot formation, and synchrotron aging. The VLA also operates over a broad range of frequencies, allowing researchers to compare young, bright jets with older, fading lobes to reconstruct a galaxy's radio history. If LOFAR is the deep bass of the cosmic orchestra, the VLA is the full symphony, offering both depth and clarity. Further south, in the Karoo Desert of South Africa, another major instrument has joined the chorus: Meerkat. This relatively new array consists of 64 dishes, each 13.5 meters wide, arranged in a spread-out pattern over 8 kilometers. Meerkat combines high sensitivity with fine resolution, operating in mid-range radio frequencies, especially useful for studying the transition zones in GRGs, where jets become lobes and where hotspots flare with sudden bursts of energy. Its dry, radio-quiet environment allows for incredibly clean observations, free from human-made interference. Meerkat has already contributed to the discovery and analysis of fossil radio galaxies, those whose central engines have long shut off but whose lobes still drift silently through space. These structures, often too faint for older telescopes to detect, now emerge in Meerkat's data like long-forgotten smoke signals. What ties all these observatories together is a commitment to interferometry, a technique that has revolutionized radio astronomy. In interferometry, each antenna or dish acts like a pixel. The signals they collect are cross-correlated with one another, combining phase and amplitude data to reconstruct an image. The larger the distance between dishes, the finer the resolution. This allows arrays like LOFAR, VLA, and Meerkat to essentially build synthetic telescopes many kilometers, or even across countries, wide. And then there's the next generation. On the horizon looms the Square Kilometer Array, SKA, a massive international effort to create the world's largest radio observatory. Once completed, SKA will span continents, linking thousands of dishes and antennas across South Africa and Australia. Its collecting area will measure over a square kilometer, making it 50 times more sensitive than current instruments. SKA will probe the early universe, the formation of the first radio galaxies, and the faintest, oldest radio lobes ever created. If GRGs like Alcyoneus are the giants we can already see, SKA will reveal the ones lost in the noise, the quietest titans whose voices have yet to be heard. But even with today's instruments, we've already transformed our understanding. Radio telescopes have shown us that the visible universe is only a slice of reality. That galaxies don't end where their stars do. That black holes are not just silent eaters, but architects of vast, invisible structures. That lobes of energy can drift across millions of light years, sculpting the intergalactic medium, influencing neighboring galaxies, and carrying with them the history of their parent black holes. Each detection is a story, a map of ancient power, of cosmic cause and effect played out over incomprehensible distances. These instruments don't just observe, they decode. They give shape to the invisible, motion to the static, and meaning to the faintest hums in space. And so, in the quest to find and understand giant radio galaxies, it is these observatories, LOFAR, VLA, Meerkat, and soon the SKA, that have become our ears to the cosmos. They've opened up a second sky. One filled with whispering giants, fossilized ghosts, and the long, slow breath of galaxies speaking across time. Beneath the grandeur of a giant radio galaxy's colossal reach lies a surprisingly organized internal structure. These aren't chaotic blasts of energy, or random outpourings of cosmic matter. Rather, GRGs are marvels of sustained, coherent processes, structured systems powered by precision and longevity. To understand how such a galaxy forms, survives, and sculpts space, we must dissect its anatomy. Like the organs of a living body, each part of a GRG plays a crucial role: the host galaxy, the jets, the lobes, and the hotspots. At the heart of every GRG lies the host galaxy, a luminous core that, in optical images, might not appear especially remarkable. These galaxies are typically elliptical in morphology, spherical or ovoid agglomerations of old stars, with little dust and no visible spiral arms. Unlike blue star-forming spirals like the Milky Way, these ellipticals shine with the yellow-orange hue of ancient stellar populations. But what they lack in youthful vigor, they make up for in mass, and more importantly, in what they host at their very centers. At the nucleus of the host galaxy sits a supermassive black hole, often billions of times the mass of our Sun. This is the engine room, the dynamo that drives the entire radio galaxy. However, not all supermassive black holes are active. In fact, most are dormant, quietly sitting at the heart of their galaxies. What distinguishes a GRG is that its central black hole is, or once was, accreting. That is, it is drawing in surrounding gas, dust, or stellar material, forming a hot accretion disk spiraling toward the event horizon. As the material heats up and twists inward, it generates powerful magnetic fields and creates the conditions necessary for launching jets. Twin beams of highly energetic particles shoot out from the poles of the black hole. These jets are among the most fascinating and mysterious structures in astrophysics. They are narrow, focused streams of relativistic plasma, composed of electrons, positrons, and possibly protons, traveling at velocities close to the speed of light. Launched from regions just outside the black hole, possibly from the inner edge of the accretion disk, or directly from the twisting magnetic fields anchored to the black hole's rotation, the jets pierce through the galactic core and emerge into intergalactic space. For a GRG to become a giant, these jets must remain coherent and stable over incredible distances. In many galaxies, jets are disrupted quickly by surrounding gas or turbulence, leading to shorter radio structures. But in GRGs, the environment is often sparse and calm, allowing the jets to maintain their shape and energy over millions of light years. The jets can remain tightly collimated for tens or hundreds of kiloparsecs before they begin to disperse and inflate the lobes. Once the jets begin to slow and interact with the surrounding medium, they terminate in regions known as hotspots. These are localized areas where the relativistic particles slam into the intergalactic gas and convert their kinetic energy into heat and radiation. The shock fronts created at these termination points are intensely energetic and glow brightly in radio wavelengths. Hotspots are typically found at the ends of jets in FR2 Radio Galaxies, a classification based on morphology, and they mark the outermost reaches of the black hole's influence. The energy from the hotspots then diffuses and expands outward into the surrounding space, inflating large, balloon-like structures called lobes. These lobes are perhaps the most iconic and visually dramatic features of GRGs. Unlike the focus jets or the compact host galaxy, the lobes are enormous, diffuse clouds of relativistic plasma, shaped by the momentum of the jet and the resistance of the surrounding intergalactic medium. Lobes can be symmetrical or asymmetrical, depending on environmental conditions. In low-density surroundings, they expand relatively unimpeded, forming smooth, rounded edges. In denser environments, they may appear warped, compressed, or bent, sometimes dramatically so. In some cases, one lobe is visibly shorter than the other, a sign that the medium on one side is denser or more turbulent, slowing expansion and disrupting flow. Inside the lobes, electrons spiral along magnetic field lines, producing synchrotron radiation, the primary source of a GRG's radio emission. Over time, these electrons lose energy and age, resulting in a fading signal known as spectral aging. By measuring the spectral gradient, how the radio emission changes across the lobe, astronomers can estimate the age of different parts of the structure, reconstructing the activity timeline of the central black hole. Some lobes even show relic structures, faint ghostly extensions from earlier activity epochs. These so-called fossil lobes are often displaced from the current jets, suggesting a period where the black hole went dormant and later reignited. In rare cases, GRGs show multiple sets of lobes, evidence of several distinct outbursts over cosmic time. This gives rise to classifications like double-double radio galaxies, where nested lobes indicate cycles of galactic activity. Between the host galaxy and the lobes lies the jet path, which can contain faint emissions known as bridges, plumes, or spines, depending on the age and structure. In some GRGs, the jets remain visible across their entire length, but in others, they become invisible, either because they've dissipated or because their orientation causes their light to be beamed away from us. Orientation, in fact, plays a key role in how we perceive GRGs. If the jets are pointed close to our line of sight, we may see a blazar or quasar, objects where the radial lobes appear foreshortened or even hidden. But when viewed from the side, GRGs reveal their full extent, their anatomy laid bare against the backdrop of the radio sky. From a distance, a GRG might look like a butterfly or a dumbbell, a central body with two vast wings stretched outward. But up close, the anatomy is precise. A central engine, hidden within an ordinary-looking elliptical galaxy. A pair of relativistic jets, launched from the black hole's poles. Hotspots, where the jets crash into surrounding space. And lobes, enormous reservoirs of energy, slowly aging as they drift into intergalactic darkness. These components don't just define the shape of the GRG, they record its history. Each structure is a phase, a footprint, a fossil of a process that began in the heart of a black hole and ended millions of light years away. Understanding the anatomy of a GRG is like reading a story written across space. The host tells us where it began. The jets reveal its energy. The hotspots trace its frontiers. And the lobes hold the echoes, fading, expanding, still glowing after millions of years. It is a story of motion, magnetism, matter, and memory. At the core of every giant radio galaxy lies a paradox. The most powerful engines in the known universe are also the most invisible. These are the supermassive black holes, regions of space so dense, so gravitationally extreme, that not even light can escape their pull. They sit silently at the hearts of their galaxies, often weighing millions to billions of times the mass of our Sun. And yet, in GRGs, these dark entities become the source of colossal outflows that stretch across millions of light years. How can something that traps light give rise to structures that shine across cosmic time? The answer lies not in what goes into the black hole, but in what happens around it. When material, dust, gas, stars, falls toward a supermassive black hole, it doesn't plunge directly inward. Instead, it forms an accretion disk, a spiraling, flattening vortex of matter that heats up as it descends. Friction and compression in the disk raise temperatures to millions of degrees, causing it to blaze brightly in X-rays and ultraviolet light. The inner regions of this disk are spinning at relativistic speeds, fractions of the speed of light. But it's not the heat alone that matters. It's the motion, the magnetism, and the violence. This rapidly spinning disk acts like a cosmic dynamo, twisting and amplifying magnetic fields to enormous intensities. And these magnetic fields are the key to launching jets. The process is complex, but it can be roughly outlined through two primary mechanisms theorized by astrophysicists: the Blandford-Zajic mechanism and the Blandford-Payne mechanism. The Blandford-Zajic mechanism is perhaps the most dramatic. It proposes that energy is extracted directly from the rotation of the black hole itself. If the black hole is spinning, and many are, some at speeds approaching the theoretical maximum, its rotational energy can interact with magnetic fields threading the event horizon. These magnetic fields act like twisted rubber bands anchored to the black hole's spin, launching jets of charged particles perpendicular to the accretion disk. In this scenario, the black hole isn't just passively feeding, it's acting like a cosmic flywheel, spinning down over time as it flings energy outward. The Blandford-Payne mechanism, meanwhile, suggests that jets may originate not from the black hole directly, but from the accretion disk itself. If magnetic fields are anchored in the spinning disk, they can sling plasma outward along their field lines, much like water sprayed from a spinning lawn sprinkler. This doesn't tap into the black hole's spin, but it can still produce powerful jets, especially in tandem with other processes. Either way, or possibly through a combination of both, the result is the formation of relativistic jets, twin beams of plasma and radiation launched along the rotational axis of the black hole. These jets are incredibly narrow at their origin, often just a few light hours or light days across, but they carry energy outward across millions of light years. The fact that something so small, a region perhaps no bigger than our solar system, can create a structure 160 times the size of the Milky Way is one of the most profound illustrations of scale in astrophysics. What powers the jets is not just the amount of material falling in, but how efficiently the system converts gravitational potential energy into kinetic energy. Supermassive black holes are astonishingly good at this. A spinning black hole accreting at high rates can convert as much as 40% of infalling mass into energy, compared to less than 1% efficiency for nuclear fusion in stars. That makes them the most efficient energy engines in the cosmos. And while it's common to imagine these jets as steady streams, they're anything but simple. Jets can fluctuate, bend, reignite, or shut off entirely, depending on the supply of fuel and the state of the black hole. Some GRGs show evidence of multiple jet epochs, separated by periods of dormancy. Others appear to have jets that wobble, perhaps due to precession of the accretion disk or perturbations caused by galaxy mergers. This variability adds layers to the story encoded in their radio lobes. Each shift in jet direction or energy output becomes a chapter in the life of the supermassive engine. It's also important to realize that these black holes don't exist in isolation. They live in galaxies, embedded in dark matter halos, surrounded by intergalactic plasma. The black hole's ability to feed, and therefore to launch jets, is often dictated by events on much larger scales. Galaxy mergers, cooling flows from surrounding gas, or tidal stripping from nearby galaxies can all funnel matter toward the galactic center, awakening a dormant black hole and triggering a new phase of jet activity. Thus, the supermassive engine is not just a cause, but also an effect, a cog in a far larger machine of cosmic evolution. Despite the violent processes involved, there's an elegance to the way these engines operate. They are governed by general relativity, magnetohydrodynamics, and quantum electrodynamics, all working in harmony. And what emerges from this blend is something profoundly powerful yet structured, beams of matter and energy that remain focused across millions of light years, tracing the cosmic environment they traverse and leaving behind lobes of radio emission that persist for hundreds of millions of years. In giant radio galaxies, the supermassive black hole is not the whole story, but it is the spark. It is the ignition switch that sets the jets in motion, that sculpts the lobes, that paints the sky in radio waves we can detect across time and space. Without these engines, there would be no GRGs, just silent galaxies drifting in darkness. But with them, you get cathedrals of energy, written across the universe in lines of force, matter, and magnetism. Emerging like cosmic lances from the heart of a galaxy, relativistic jets are among the most spectacular and mysterious phenomena in the known universe. In giant radio galaxies, GRGs, these jets are not fleeting bursts of energy, they are sustained streams, often maintained for tens to hundreds of millions of years, reaching out across intergalactic space. Though they originate in regions barely larger than our solar system, they can grow to stretch across millions of light years, carving channels through the cosmos, and leaving behind enormous lobes that continue to glow long after the jets themselves have faded. To grasp the importance of relativistic jets, we must first understand what the term really means. Relativistic refers to velocities that are a significant fraction of the speed of light. In the case of AGN, active galactic nucleus, jets, this can mean anywhere from 70% to more than 99% of light speed. At such speeds, relativistic effects, those predicted by Einstein's theory of special relativity, become significant. Time dilates. Mass increases. Radiation is beamed forward in tight cones. These effects aren't just mathematical, they influence what we observe, how we observe it, and what they mean physically for the structures they produce. When the central black hole of a GRG is active, fueled by infalling gas and spinning rapidly, it can launch two opposing jets from its poles. These jets are tightly collimated, meaning they remain narrow and focused even across vast distances. They consist of plasma, highly energetic particles, usually electrons and positrons, although the composition may include protons as well. These particles are accelerated to near light speed and confined by twisted magnetic fields, forming beams that shoot through the galaxy and far beyond. The narrowness of the jets is one of their most striking features. In some cases, they remain focused for hundreds of thousands of light years before dispersing. This level of collimation suggests a high degree of internal structure, complex magnetic field configurations and particle dynamics that remain coherent over immense timescales. For comparison, if a jet launched from the center of our Milky Way, and it stretched 1 million light-years without widening more than a few hundred light-years, it would pass dozens of galaxies before it even began to spread. The precision is staggering. But the jets don't travel through empty space. They encounter interstellar and intergalactic media, tenuous clouds of gas, dark matter, and plasma that fill the universe. As they move outward, jets plow through this material, heating it, pushing it aside, and sometimes entraining it. The resistance they face can bend, slow, or even disrupt them. Some jets are one-sided in appearance, not because the other jet doesn't exist, but because of relativistic beaming. The forward-moving jet appears brighter due to the Doppler effect, while the receding jet becomes dimmer and may disappear entirely from view. The journey of a jet is not always smooth. Many display knots, wiggles, and shocks, features that reveal instabilities or changes in energy flow. These may be caused by fluctuations in the black hole's output, interactions with surrounding matter, or even precession of the accretion disk, which causes the jet's direction to slowly shift over time. In some GRGs, these instabilities can create S-shaped jets or multiple bends, an almost artistic signature of chaotic, yet persistent, motion through space. At the end of their journey, when the jets finally decelerate, often after traveling hundreds of kiloparsecs, they form termination shocks, where their energy is dumped into surrounding space. These are the hotspots, visible as bright nodes in radio images. The decelerated plasma then spreads out, forming the lobes that define the outermost edges of the GRG. But the journey of a jet is also a history of its black hole's feeding habits. A powerful, steady jet indicates consistent accretion, while fading or disrupted jets may signal that the central engine has gone dormant. Some jets even show signs of intermittency, firing on and off like a cosmic engine sputtering over millions of years. When jets restart after a long pause, they can drill fresh channels through previously inflated lobes, creating double-double radio galaxies, with two distinct pairs of lobes representing multiple epochs of activity. Interestingly, the behavior of relativistic jets is also tied to the spin of the black hole. Faster spins mean more efficient extraction of rotational energy, potentially resulting in more powerful jets. In this way, the characteristics of a jet can reveal deep information about the black hole that launched it, even though the black hole itself remains unseen. The effects of jets are not limited to their own galaxy. As they carve through space, jets can heat intergalactic gas, trigger or quench star formation, and redistribute magnetic fields. They can even influence the evolution of neighboring galaxies, especially in cluster environments. Over millions of years, a jet from one GRG can sculpt an entire region of space, altering its chemistry, structure, and dynamics. It's as if the black hole, through its jets, is sculpting space itself. And yet, for all their power, relativistic jets are fragile, too. Disruptions in magnetic alignment, sudden drops in fuel, or collisions with dense gas clouds can bring a jet to an end. When that happens, the lobes begin to fade, the hotspots cool, and the once powerful beacon of energy becomes a fossil, a silent memory of former glory. But while they last, relativistic jets are the most focused expressions of energy the universe produces. They serve as conduits, linking the unimaginable gravity of a black hole with the vast emptiness of space. They are bridges of motion, light, and time. From a central point no larger than the orbit of Neptune, a black hole can launch particles that race across the cosmos, carrying with them the story of their origin. In giant radio galaxies, these jets are the arteries, beating outward, pumping energy into the lobes, sustaining the galaxy's radio glow for eons. Without them, the GRG would have no wings. With them, it becomes a force felt across millions of light years. To truly understand the ghostly glow of giant radio galaxies, we must follow a trail that leads deep into the invisible fabric of the cosmos, a trail woven by magnetic fields and lit by a process called synchrotron radiation. This is the mechanism by which GRGs, invisible in ordinary light, become radiant giants in the radio sky. It's a phenomenon that transforms streams of charged particles into cosmic lighthouses, whispering across the electromagnetic spectrum with a voice that only radio telescopes can hear. At the heart of it all are electrons, tiny, negatively charged particles that travel at nearly the speed of light through the vast jets and lobes of radio galaxies. These electrons aren't moving in straight lines. Instead, they spiral, curve, and twist as they navigate through tangled webs of magnetic field lines. And this dance, the curved motion of relativistic particles through magnetic fields, is what produces synchrotron radiation. To visualize it, imagine a particle hurtling through space. In the absence of any magnetic fields, it would continue in a straight line forever. But introduce a magnetic field, and that same particle is forced to curve, its path bent into a helix. Now speed that particle up to relativistic velocities, near the speed of light, and something remarkable happens: it begins to radiate energy. Not in all directions, but in a focused beam, perpendicular to its spiral path. That beam is synchrotron emission, and it is the primary light source of giant radio galaxies. The energy of synchrotron radiation doesn't show up in visible light. It appears in the radio portion of the electromagnetic spectrum, and sometimes in X-rays and infrared depending on particle energies and magnetic field strengths. This means that entire structures, lobes spanning millions of light years, can remain completely invisible to human eyes, optical telescopes, or even infrared surveys. But in radio frequencies, they glow like lanterns. What gives this emission its character is a combination of two factors: the energy of the electrons and the strength of the magnetic fields. Higher energy electrons, spiraling through stronger magnetic fields, produce higher frequency radiation. We can actually determine the age of the particles in a lobe by examining their synchrotron spectrum. As electrons radiate energy, they lose speed, and therefore begin to emit lower and lower frequency radiation. This gradual decline is known as synchrotron aging, and it creates a spectral gradient across the lobes of a GRG. By measuring this gradient, astronomers can estimate how long ago the black hole launched the particles, how powerful the original jets were, and even how quickly the electrons are diffusing through space. In this way, synchrotron emission becomes a kind of cosmic clock, ticking down the lifetimes of invisible storms launched millions of years ago. But where do these magnetic fields come from? That question is more complex, and still partially open. The prevailing theory is that magnetic fields originate in the accretion disk and jets of the black hole. As plasma moves in tight spirals around the black hole's event horizon, it generates toroidal, donut-shaped, magnetic fields. These fields are then wound tighter and amplified by the rotation of the disk and the spin of the black hole itself. When the jets launch, they carry these fields with them, threading the jets like steel cables, guiding the flow of plasma, and confining it into a narrow beam. Once in the lobes, the magnetic fields begin to tangle and expand. Unlike the highly ordered fields near the jet base, lobe fields are more chaotic, spread across vast regions, stretched and compressed by turbulence and interaction with the intergalactic medium. But they're still strong enough to keep electrons spiraling and emitting. In some parts of the lobe, the magnetic fields align, creating polarized radiation, a signature that astronomers use to map the field orientation. These polarization maps reveal vast swirling patterns, shocks, and even shear flows within the lobes, giving us a window into the invisible physics sculpting the radio emission. The brightness of synchrotron radiation is proportional to the number of relativistic electrons and the strength of the magnetic field. But it fades over time. As electrons lose energy, they stop emitting. This is why older GRGs often have faint, diffuse lobes with little to no visible jet structure, a sign that the jets have shut off, and the remaining electrons are coasting into silence. However, sometimes magnetic reconnection events or turbulence can reaccelerate electrons within the lobes, giving rise to patchy reillumination, like sparks in dying embers. In some cases, lobes are seen far from any obvious host galaxy. These are called orphan lobes or fossil radio sources, and they're often only detectable at very low frequencies, the last whisper of electrons losing their final fractions of energy. LOFAR and other low-frequency observatories have become essential for finding these ghosts, whose synchrotron glow is so faint that it disappears at higher radio bands. One fascinating feature of synchrotron radiation is its non-thermal spectrum. Unlike blackbody radiation from stars, which has a smooth, bell-shaped curve, synchrotron spectra follow a power law, meaning that they decrease steadily with increasing frequency. This non-thermal signature is how astronomers know they're looking at relativistic processes, rather than thermal ones. It's a fingerprint of speed, curvature, and magnetism, nothing like the soft glow of starlight. Altogether, synchrotron radiation is the voice of giant radio galaxies. It is how they speak across time. Every arc of glowing plasma, every lobe, every fading filament, is a message encoded in magnetic spirals. Without this process, GRGs would be undetectable. Their vastness would be hidden. Their energy would be silent. But thanks to this one mechanism, relativistic electrons spiraling through ancient magnetic fields, the universe is filled with whispers. Whispers from galaxies long dormant. Whispers from black holes that once roared. Whispers that, even now, travel millions of light years just to reach us. If the central black hole is the heart of a giant radio galaxy, and the jets are its arteries, then the lobes are the massive lungs, vast, ballooning reservoirs where the energy finally gathers, accumulates, and radiates into the cosmos. These cosmic lobes are what make giant radio galaxies visible across millions of light years, glowing not with starlight, but with the faint hum of synchrotron radiation. They are the grand, swollen echoes of a black hole's fury, sculpted by time, magnetic fields, and the tenacious push of relativistic plasma against the intergalactic dark. When the jets, launched at near light speed from the supermassive black hole, travel far from the host galaxy, they eventually slow down. This deceleration can be sudden, crashing into denser regions of space, or gradual, fading as the jets expend their energy. At these termini, the jet material spills outward, forming termination shocks, the hotspots, and from there, expands into vast, diffused lobes. These lobes, sometimes symmetrical and sometimes wildly asymmetric, are the most dominant structures in a GRG, often accounting for over 90% of the visible radio emission. The size of these lobes is staggering. In Alcyoneus, the current record holder, the lobes span nearly 16 million light-years, more than 150 times the diameter of the Milky Way. They can engulf galaxy groups, stretch across cosmic filaments, and extend so far that they begin to curve and warp under the influence of larger-scale cosmic structures like intergalactic winds or galaxy cluster fields. Yet despite their size, these lobes are incredibly tenuous. Their densities are often lower than even the near vacuum of intergalactic space, just a wisp of relativistic particles and magnetic fields, expanding slowly over hundreds of millions of years. It's this tenuousness that makes them difficult to detect in anything other than radio wavelengths. They don't glow in optical or X-rays. They don't block light like dust. Their presence is entirely non-thermal, invisible except to instruments that can hear the faint whisper of spiraling electrons. Inside the lobes, the energy is not evenly distributed. There are regions of turbulence, filaments, and knots, zones where magnetic fields have compressed or where old plasma has been re-energized. Some lobes appear to have internal shocks, while others show filamentary arcs, tracing the pathways of past jet disruptions or changes in direction. In some GRGs, the lobes are sharply defined, almost like cosmic bubbles. In others, they fade gradually into the void, the product of long, gentle diffusion. Interestingly, the morphology of the lobes can tell us a great deal about the history of the black hole and its jets. In so-called FR2 radio galaxies, named after the Fanneroff-Riley classification, lobes are typically edge-brightened, meaning the brightest emission occurs at the outer rim, near the hot spot. This indicates powerful, ongoing jet activity where energy continues to be pushed outward. In FRI galaxies, the lobes are brightest near the core and fade outward, a sign that the jets have weakened or that turbulence is disrupting the flow. GRGs tend to exhibit FR2 characteristics, suggesting they result from prolonged, stable jet launching over immense time frames. Another aspect that defines these lobes is their spectral age. As the relativistic electrons emit synchrotron radiation, they lose energy. Higher energy electrons fade first, leaving behind lower frequency radiation. By mapping the radio spectrum across a lobe, from high to low frequency, astronomers can trace the age of the plasma, identifying which regions are young and which are old. This allows scientists to reconstruct the sequence of events, when the jets were strongest, when they shifted, and when they eventually weakened or ceased altogether. There's also the matter of buoyancy. Over cosmic timescales, lobes may rise through the intergalactic medium, especially in cluster environments. As they drift, they can displace hot gas, create cavities, and stir up turbulence in nearby intergalactic plasma. These motions have been detected in galaxy clusters through X-ray observations, where the absence of gas in certain regions matches up with the position of ancient radio lobes. This reveals that the energy in the lobes isn't just passive, it's mechanically active, capable of shaping the environment around it. In some cases, lobes can even trigger or suppress star formation in nearby galaxies. As they sweep through space, their shock fronts can compress gas clouds, causing them to collapse into stars. Alternatively, the heat and turbulence they introduce can disperse gas, preventing stars from forming. Thus, GRGs don't just sit in space. They influence the evolution of everything around them. Then there are the truly ancient lobes, the fossil lobes. These are structures that remain after the central black hole has gone quiet. They no longer have active jets feeding them. Their hotspots have faded. Their plasma has cooled. But under the right conditions, they still emit faint, low-frequency radio waves. Discovering these fossils requires extremely sensitive instruments tuned to the lowest ends of the radio spectrum, such as LOFAR. Fossil lobes are cosmic relics, remnants of radio galaxies that were active perhaps a billion years ago. Studying them is like listening to a cosmic echo, the last whispers of a story that began long before Earth even existed. What makes all this possible, what holds the lobes together and allows them to radiate across such timescales, is the interplay of magnetic fields and relativistic particles. Without these, the jets would dissipate, the plasma would vanish, and the energy would blend invisibly into the void. But instead, the lobes persist. They live long after the jets die. They grow and stretch, age and fade, but they remain, monuments to a black hole's ancient breath. In the grand tapestry of the universe, these lobes are like strokes of paint from an invisible brush. They trace the presence of powerful engines that once lit up their galaxies. They map the movements of matter and magnetism across intergalactic space. And they carry with them a story of creation, expansion, and eventual silence, a narrative written not in light, but in radiation and field. In their scale, they humble the imagination. In their persistence, they challenge the notion of decay. And in their silence, they teach us that not all power shouts. Some of it echoes, endlessly, through the fabric of space. Giant radio galaxies may stretch across millions of light years, but their immense size belies a fragile and intricate life cycle. Like living organisms, they are born, grow, thrive, weaken, and eventually fade into obscurity. This evolution unfolds not over decades or centuries, but across hundreds of millions, sometimes billions, of years. Their grandeur is matched only by their slowness, each stage unfolding on a timescale that dwarfs human history and even the lifetimes of entire species. The birth of a giant radio galaxy begins with the awakening of its central black hole. For most of its life, a supermassive black hole may remain quiescent, quietly sitting in the nucleus of its host galaxy. But when conditions change, perhaps due to a galactic merger, the cooling of a gas halo, or accretion from a disrupted companion, the black hole becomes active. As matter spirals in, an accretion disk forms, and with it comes the launch of relativistic jets. These jets signal the start of the active phase, the moment when a galaxy begins to carve out its place as a radio-emitting titan. Early in its active life, the radio galaxy may appear compact. The jets have not yet traveled far. Their termination shocks and lobes remain close to the galactic center. These are known as compact steep spectrum sources or young radio galaxies. Over time, as the jets continue to inject energy into the surrounding medium, the lobes begin to expand, growing in both volume and brightness. As the jets maintain their output and punch through the intergalactic medium, the galaxy enters its growth phase. This is when the classic double-lobed shape becomes more pronounced, and the radio galaxy may begin to extend hundreds of thousands, even millions, of light years. During this stage, hotspots at the ends of the jets are still prominent, bright beacons where the jets are actively depositing their energy. The structure is sharply defined, symmetrical or nearly so, and the entire system blazes with radio light. For a radio galaxy to become giant, it must sustain this growth for an extraordinary amount of time. This requires a delicate balance. The black hole must continue accreting material at a steady rate. The surrounding environment must be sparse enough to allow the jets to extend unimpeded, and the magnetic fields must remain strong enough to confine and direct the plasma. It is during this prolonged activity that a radio galaxy may cross the threshold from large to giant, reaching sizes of over 1 million light-years, and in rare cases, pushing toward the 10 million light-year mark or beyond. But no engine runs forever. Eventually, the supply of fuel to the central black hole begins to dwindle. The reasons for this vary. Perhaps the merger that once fed the core has ended, or the gas halo has been exhausted or expelled. When accretion slows, so too does jet production. This begins the dormancy phase, when the once vibrant jets weaken, flicker, and finally shut off. Without the steady injection of energy, the lobes stop expanding. The hotspots fade. The once orderly streams of plasma become turbulent, diffuse, and spectrally aged. What remains is a fossil radio galaxy, a vast structure still glowing faintly in radio wavelengths, but slowly decaying. The synchrotron emitting electrons inside the lobes begin to lose energy. Higher energy particles radiate away their power first, leaving only low-frequency emissions. Over tens to hundreds of millions of years, even these emissions begin to fade, and the lobes may become invisible at all but the lowest radio frequencies. In this fossil phase, the radio galaxy becomes a ghost of its former self. If no new jets reignite, the lobes will continue to expand passively, their edges softening as the plasma disperses into the surrounding intergalactic medium. The magnetic fields become more chaotic, the relativistic particles spread thin, and the last traces of the galaxy's former might gradually dissolve into the cosmic background. But this is not always the end. In some rare cases, a dormant radio galaxy may reignite. If new material finds its way into the central black hole, through a merger, tidal interaction, or cooling gas accretion, the jets can resume. When this happens, a fresh pair of jets punches through the fossil lobes, creating a phenomenon known as a double-double radio galaxy, one set of older lobes nested within a newer, smaller pair. This is a sign that the black hole has gone through multiple active cycles, each leaving behind its own imprint on the cosmos. Overall, the lifespan of a GRG is measured not just in size, but in phases. 1. Ignition. The black hole awakens and launches jets. 2. Growth. Jets inflate lobes and carve through intergalactic space. 3. Maturity. The radio structure reaches its largest extent. 4. Dormancy. The jets shut down, the lobes begin to fade. 5. Fossilization. Energy disperses. The structure becomes ghostly and cold. 6. Possible rebirth. The cycle may restart with renewed activity. Each phase is a cosmic chapter, played out over timescales that challenge comprehension. While stars burn out in millions to billions of years, and galaxies evolve slowly over cosmic epochs, the story of a giant radio galaxy is one of sustained violence and gradual decay, an arc that spans the history of the universe itself. And though they may fade from visibility, the imprints of GRGs linger. The lobes leave behind magnetized relics, they stir and heat the intergalactic medium, they alter star formation in their vicinity, and they provide clues to the behavior of black holes over cosmic time. In this way, the end of a GRG's active life is not its true death, but a transformation, from engine of energy to relic of memory. Giant radio galaxies don't go out with a bang. They go out with a whisper, fading slowly into the quiet afterglow of a universe that never forgets. When a giant radio galaxy falls silent, the universe doesn't forget. Long after the jets have stopped firing and the central engine has gone dark, its fingerprints remain smeared across the fabric of intergalactic space. These lingering echoes are called fossil radio galaxies, vast, fading structures where ghostly lobes still drift through the cosmic void, carrying the last remnants of a black hole's ancient outburst. Though the violence is over, the memory remains etched in magnetic fields and radio waves that still hum faintly, long after the central galaxy has gone still. The transformation into a fossil begins the moment the jets cease. Without the relentless pressure of energy being funneled from the black hole into the lobes, the entire system begins to coast. The hotspots, those intensely bright regions at the termination points of the jets, are the first to fade. Their brilliance depends on continuous injection of plasma at nearly light speed. Cut off from their source, they cool rapidly, and within a few million years, they become indistinct, swallowed by the diffuse glow of the lobes. Next, the lobes themselves begin to relax and expand. While still magnetized and filled with relativistic particles, they are no longer confined by active jets. The internal pressure drops. The plasma begins to disperse, and the lobes start to lose their sharp edges. Their brightness declines steadily, especially at higher frequencies, due to the process of synchrotron aging. High-energy electrons radiate away their energy quickly, meaning that the radio spectrum softens. What was once a brilliant source across a wide band of frequencies becomes detectable only at the lowest radio wavelengths. This fading spectrum is more than just a technical observation, it is a timeline, a chronicle of the decay. By analyzing the radio spectral index, astronomers can determine not just the age of the lobes, but how long it has been since the jets were last active. The steeper the spectral index, the older and more depleted the electron population. In the most ancient fossils, the lobes can be nearly invisible across most of the radio spectrum, requiring instruments like LOFAR, the low-frequency array, to detect their faint whisper below 100 MHz. Despite their near invisibility, fossil radio galaxies are still enormous. Many retain their original structure, with lobes stretching across millions of light-years. Some appear as disconnected clouds, no visible host galaxy, no jets, just irregular patches of weak emission floating in space. These, orphan lobes, are among the most enigmatic objects in radio astronomy. They are the cosmic ruins left behind when the parent galaxy has moved on, merged, or simply become too faint to trace. Finding the host galaxy in such cases becomes a puzzle, sometimes solved by matching the lobe's orientation or polarization vectors with nearby elliptical galaxies. In the most extreme examples, fossil lobes may persist for over 1 billion years. During that time, they don't simply sit in place. They can drift slowly through the intergalactic medium, rise buoyantly in galaxy clusters, and become entangled with other structures. X-ray observations sometimes reveal cavities in hot gas where radio lobes once existed, silent voids, evacuated by ancient jets and now filled with cooler plasma or rising like bubbles in a thermal bath. Some fossil lobes show signs of reillumination. This can happen through shock waves, perhaps from a nearby galaxy collision or cluster merger, that re-energize electrons trapped in the lobe. Alternatively, turbulence or magnetic reconnection inside the lobes may accelerate particles once more, causing faint rebrightenings or patchy emission across the structure. These flashes are brief and rare, but they hint that fossil radio galaxies aren't always completely dead. They can flicker, if only briefly, like embers stirred in the dark. In other instances, the central black hole itself reignites, launching new jets into old lobes. This produces double-double radio galaxies, systems where a younger pair of inner lobes expands inside a larger, older pair. The outer lobes represent a previous outburst, now fossilized, while the inner pair marks the beginning of a new cycle. This phenomenon offers stunning insight into the episodic nature of black hole activity, suggesting that some GRGs don't live once, but live many times. Fossil radio galaxies also play a critical role in cosmic archaeology. They act as time capsules, preserving the conditions of intergalactic space from an earlier era. By studying the shape, size, and spectral properties of fossils, astronomers can infer not only the history of a particular galaxy, but also the density, temperature, and magnetic conditions of the intergalactic medium at the time the jets were active. These relics are more than remnants. They are maps of the invisible environment through which they expanded. Detecting fossils is a growing field in radio astronomy. With next-generation low-frequency telescopes like LOFAR, MWA, and eventually the Square Kilometer Array, SKA, astronomers are uncovering a hidden population of ancient radio lobes previously missed by older surveys. Many of these fossils are huge, faint, and far from their parent galaxies, suggesting that the universe is filled with the ghosts of dead giants, remnants of active galactic nuclei that once reshaped the cosmos, now drifting silently, remembered only in radio. They may not blaze brightly anymore. They may not command the skies with their jets or shake the intergalactic medium with their outflows. But fossil radio galaxies are still present, still whispering, still echoing the story of the universe's most powerful engines, long after those engines have gone cold. For all their grandeur, giant radio galaxies remain puzzlingly rare. Among the billions of galaxies scattered across the cosmos, only a tiny fraction manage to evolve into these immense, sprawling giants with radio lobes that stretch across millions, even tens of millions, of light years. This rarity raises a fundamental question: why do only a select few galaxies reach such colossal scales, while the vast majority remain relatively modest in their radio dimensions? What cosmic recipe allows some to grow into giants, while others fizzle out early? The answer lies not in a single factor, but in a complex symphony of conditions, some intrinsic to the galaxy itself, others dictated by the surrounding universe. To begin with, one of the primary contributors is the activity cycle of the central black hole. For a galaxy to become a GRG, its black hole must not only be supermassive, often billions of solar masses, but it must also be sustained in its activity for hundreds of millions of years. Most galaxies experience active phases that are short-lived, perhaps just a few million years, before the black hole's accretion flow declines and the jets switch off. Without continuous feeding, the lobes never reach full size. They stall, fade, and shrink from visibility. Sustaining that activity requires a steady supply of fuel. This could come from cold gas funneled into the core during a merger, a galactic collision, or a cooling flow in a massive halo. But not all galaxies have access to such fuel, and even those that do may have it disrupted by feedback processes, like the black hole heating its own surroundings, shutting off its own supply. This delicate balance, between feeding and self-limiting, is likely one of the main reasons why many potential giants never grow past adolescence. But internal factors are only half the story. A galaxy might be perfectly capable of launching powerful jets, but whether those jets can expand into large-scale lobes depends critically on the environment beyond the galaxy, the intergalactic medium, IGM. If the jets plow into a dense or turbulent region, like a galaxy cluster filled with hot X-ray gas, they can be quickly slowed, bent, or dissipated. This leads to radio galaxies that are compact or distorted, unable to grow large. On the other hand, if a galaxy finds itself in a low-density region, such as a cosmic void or filament, the jets can expand much more freely, encountering less resistance, and pushing their lobes farther into intergalactic space. This environmental dependence is supported by observations. Many of the largest GRGs are found in relatively isolated environments, far from crowded clusters, where intergalactic resistance is minimal. In these rare, quiet stretches of space, radio lobes can balloon outward for hundreds of millions of years without being prematurely quenched. In contrast, galaxies buried in dense cluster environments may launch powerful jets that struggle to grow beyond a few 100,000 light-years before being strangled by pressure and turbulence. Another factor may be black hole spin. The spin of a supermassive black hole can determine how efficiently it converts accreting mass into jet energy. A rapidly spinning black hole, due to the frame-dragging effects described by general relativity, can produce more powerful, more collimated jets than a slowly spinning one. If only a subset of black holes are spinning fast enough, and if that spin can be maintained over long durations, then only those systems would have the potential to evolve into full-fledged GRGs. This introduces an element of cosmic chance, as spin is determined by a galaxy's entire merger history, accretion history, and even chaotic angular momentum exchanges. We also need to consider the orientation of the jets relative to the host galaxy and our line of sight. Jets launched at an angle through a dense galactic plane may lose energy faster due to drag from surrounding stars and gas. Jets angled away from the densest regions may survive longer. Additionally, orientation affects what we observe. If a GRG is aligned with its jets pointing directly at us, relativistic effects like Doppler boosting may alter our measurements, causing us to underestimate its true size unless carefully corrected for. There's also the matter of time. GRGs take hundreds of millions of years to reach their full extent. So it's not just a question of which galaxies can become giants, it's also a question of when. Some galaxies might be on their way to becoming GRGs but haven't had enough time yet. Others may have already gone through a giant phase and faded into fossilhood, their lobes now too faint to detect. In this sense, observational bias becomes critical. We only see GRGs during a brief window when their lobes are large and still radiating at detectable levels. This may mean that they're more common than we think, but only a small percentage are caught in the act. Technological limitations also play a role. For decades, radio surveys were biased toward compact, bright, high-frequency sources, missing the fainter, more extended structures of GRGs, especially those with aged lobes emitting mostly at low frequencies. With the advent of telescopes like LOFAR and upcoming instruments like the Square Kilometre Array, we're beginning to detect many more giants and fossils, suggesting the population may be significantly undercounted. As sensitivity improves, and as sky coverage expands at lower frequencies, we may find that GRGs are the hidden majority among large radio galaxies, simply lost in the noise until now. Finally, there's the question of cosmic evolution. The universe was more compact and denser in its earlier epochs. Galaxies formed closer together, and intergalactic space was filled with denser gas. This would have made the conditions for GRG growth more hostile in the early universe. As the universe expanded and the cosmic web stretched out, more room and lower densities may have made it easier for GRGs to form. Thus, the emergence of giants may be more likely in later cosmic times, which is precisely when we are observing them now. This adds another layer of rarity. Only galaxies of the right mass, in the right epoch, with the right spin, in the right environment, fed for long enough, can evolve into true giants. In the end, the mystery of their size is not due to any single trait, but to a perfect storm of cosmic alignment. A galaxy with a massive black hole that spins fast, lives in an environment that offers little resistance, has access to a steady diet of fuel for millions of years, and is lucky enough not to be disrupted by nearby galaxies or turbulence. Only then can it build the towering lobes we associate with GRGs. It's a cosmic lottery, and only a few galaxies hold the winning ticket. Beyond the boundary of any galaxy lies a realm not empty, but thinly filled, a vast expanse of sparse, ionized gas, magnetic fields, and dark matter filaments known as the intergalactic medium, or IGM. Though diffuse, this cosmic environment plays an outsized role in the destiny of giant radio galaxies. It is not simply the background against which jets unfold, it is the arena, the resisting medium, the sculptor and sometimes the saboteur of the titanic structures these galaxies strive to build. To understand how a radio galaxy becomes truly giant, one must look at how its relativistic jets interact with the IGM over hundreds of millions of years. The jets themselves begin as tightly collimated streams of plasma, energized by the black hole and guided by magnetic fields. But these jets do not travel in a vacuum. They must punch their way through the galactic halo and then into the intergalactic space beyond. Here, the density, pressure, and structure of the IGM determine just how far those jets can go, and in what form they will arrive. In dense environments, such as the cores of galaxy clusters, the IGM is filled with hot X-ray emitting gas, at temperatures of millions of degrees. Jets that try to expand into this medium face immense external pressure. The plasma slows, spreads, and can be deflected, forming shorter, more distorted radio lobes. This is why many radio galaxies found in clusters are compact or bent, the classic head-tail or narrow-angled tail morphologies where jets are curved backward like a cosmic windsock, shaped by the motion of the host galaxy through the cluster gas. But in less crowded, lower-density environments, like the outskirts of clusters, galaxy filaments, or even cosmic voids, the IGM is far less obstructive. It lacks the pressure and turbulence to choke the jets or squash the lobes. Instead, the plasma flows outward with relative ease, inflating huge lobes that can continue to expand for hundreds of millions of years with little resistance. These are the birthplaces of giant radio galaxies. Observations have shown that many GRGs tend to avoid galaxy cluster centers and instead appear in the peripheries or even isolated regions, where the IGM is thinner and more uniform. This isn't coincidence, it's the freedom of the intergalactic medium that allows these structures to stretch so far. In some cases, a lobe on one side of a GRG is significantly longer than the other, not because the jets themselves are asymmetric, but because one side is moving through denser or more turbulent IGM, while the other is sailing through thinner, quieter space. The IgM also affects jet stability. In turbulent or high-pressure regions, jets are more prone to instabilities. They kink, wobble, or break up, leading to more chaotic lobe structures. But in calm, homogeneous environments, the jets remain laminar, smooth, narrow, and collimated, maintaining their focus across vast distances. This sustained focus allows the jets to deposit energy more efficiently into the lobe's edges, inflating them faster and with more definition. Temperature is another crucial factor. In hot, dense environments, the ambient pressure may compress the expanding lobe, slowing its growth and causing it to mix with the surrounding gas. But in the cooler stretches of the cosmic web, regions where the IgM is more tenuous and less heated, the pressure is lower, and lobes can expand adiabatically, retaining more of their shape and internal pressure as they grow. The magnetization of the IgM is still poorly understood, but it likely plays a role as well. If the intergalactic medium is threaded with weak magnetic fields, as some simulations and polarization studies suggest, then these fields can influence how the radial lobes evolve. Weak magnetic environments may allow the lobes to expand more isotropically, while stronger fields may channel their growth in particular directions. These large-scale magnetic filaments, sometimes stretching over megaparsecs, could act like rails or fences, subtly steering or containing the expansion of GRGs. There is also evidence that the IgM acts not just as a passive medium, but as a canvas upon which the past is written. Fossil radial lobes drifting through the IgM have been observed to create cavities in hot gas, visible in X-ray images. These bubbles, devoid of thermal particles, reveal that the IgM has been displaced, reshaped, and even reheated by the passage of old radio galaxies. In this sense, the IgM doesn't just influence GRGs, it remembers them. And the reverse is true, GRGs can probe the IgM. Because their lobes trace the density and pressure of the surrounding environment, they become tools of cosmic cartography, revealing the texture of the invisible medium. By studying how radio lobes bend, break, brighten, or fade as they move through space, astronomers can infer the properties of the IgM, its density gradients, temperature fluctuations, and even the direction of intergalactic winds. In essence, GRGs are cosmic wind tunnels, testing the conditions of the medium as they grow. Perhaps the most fascinating implication is this: if the IgM were more hostile, more uniform, more pressurized, more chaotic, GRGs might not exist at all. Their presence is a kind of accident, or a luxury afforded by the quiet spaces between the louder nodes of the cosmic web. They are not just powered by black holes, they are enabled by emptiness, by the space between things, by the silence into which they grow. It's a reminder that in the cosmos, as in life, growth is not only a function of inner strength, but of external peace. Only in the calmest corners of the universe do galaxies whisper outward and become giants. The story of a giant radio galaxy does not always end in silence. In some extraordinary cases, these cosmic titans rise from their own ashes, reawakening in a display of renewed violence that defies the long dormancy of their past. This phenomenon, known as AGN reactivation or restarting activity, presents a remarkable twist in the life cycle of galaxies, showing that one galaxy may undergo multiple jet outbursts over cosmic time, separated by millions or even hundreds of millions of years. The evidence for this rebirth isn't theoretical. It's been captured in the skies, traced in radio waves that reveal galaxies with not just one pair of radio lobes, but two, or sometimes more. These are the so-called double-double radio galaxies, GRGs, and they are among the clearest indicators that active galactic nuclei, AGN, can shut down and later reignite, launching entirely new episodes of jet activity. A GRG appears as a central galaxy with two concentric pairs of lobes. The outer lobes are vast, diffuse, and typically older, showing signs of synchrotron aging, faded emission, steep radio spectra, and irregular structure. The inner lobes, by contrast, are younger, more compact, and often brighter, with well-defined hotspots and active jets still visible. This layered configuration is like reading a book with chapters, each set of lobes marking a distinct period of activity separated by a long pause in between. How does this happen? The central black hole, despite going dormant, never truly dies. It's not a star that burns out, but a gravitational well that can always be reignited given the right conditions. Sometimes, fresh material falls inward again, perhaps after a galaxy merger, a tidal disruption event, or simply the slow return of cooling gas in the galactic halo. This renewed accretion feeds the black hole's engine, and the jets roar back to life, carving new paths into space, often not quite aligned with the old ones, especially if the black hole's spin axis has changed over time. Astronomers have identified several such galaxies. One notable example is J1835 plus 6204, a GRG whose two generations of lobes span vastly different sizes. The outer lobes extend over nearly 1 million light-years, while the inner pair is just beginning to grow, barely a fraction of that distance. Another is B0925 plus 420, which exhibits not just 2, but 3 distinct pairs of lobes, a triple-double radio galaxy. These systems offer a rare glimpse into the episodic nature of AGN, like cosmic geysers that erupt again and again, separated by eons of calm. This restarting behavior raises compelling questions. What determines the length of the quiet phase? Is it the availability of fuel, or something more complex, like the reorganization of magnetic fields, or the repositioning of accretion flows? Why do some galaxies restart while others fade completely? And what happens to the fossil lobes when a new pair of jets is born? Do they interact? Collide? Or do they expand independently, ghosts from different eras layered upon each other? There are even cases where the new jets seem to drill through the old lobes, re-energizing patches of fossil plasma as they pass. In these hybrid systems, the old and the new coexist, sometimes mingling, sometimes interfering. The result is a chaotic, tangled structure of emission that defies easy categorization, and serves as a natural laboratory for understanding how jets propagate through previously energized media. This idea of episodic AGN activity also fits with models of galaxy evolution. Galaxies are dynamic systems, influenced by mergers, starbursts, feedback processes, and inflows from the cosmic web. It's natural to expect that their central black holes might cycle between active and dormant states, depending on the state of the host galaxy. In this sense, GRGs that restart aren't unusual. Their timelines, revealing that black hole activity is not a singular event, but a repeating pattern, driven by the chaotic dance of matter in the universe. And it's not just the radio lobes that bear the signature of this rebirth. Some restarting AGN show optical or X-ray flares, or changes in ionization levels in nearby gas clouds. These provide cross-wavelength clues that a black hole is turning back on, adding even more evidence that rebirth is not only possible, it might be common. Yet there's still mystery. In many GRGs, the inner and outer lobes are misaligned, suggesting the black hole's spin axis has precessed or tilted. Could mergers or internal dynamics have reoriented the black hole's angular momentum? If so, each new jet cycle might carve a different path, like the pen of a scribe writing new lines over old ones, forming elaborate, multi-lobed signatures in the sky. With advancing technology, more of these galaxies are being uncovered, especially by low-frequency surveys that can detect the ancient outer lobes alongside their younger counterparts. Instruments like LOFAR, GMRT, and the upcoming SKA are making it easier to capture the full history of these galaxies in a single image, a living fossil, layered in radio light. These galactic rebirths remind us that in the universe, endings are often only intermissions. A black hole that sleeps for 100 million years may still wake again, and a galaxy that faded into radio silence may once more roar across the sky, carving new lobes and telling new stories. The cosmos is not static. It pulses, pauses, and returns, forever writing and rewriting itself in jets and lobes, in silence and in sound. For decades, giant radio galaxies were thought to be rare, enigmatic outliers, exceptional in their scale, and limited in number. But as our observational technology has sharpened and our surveys have reached deeper into the cosmos, a more complex and intriguing possibility has emerged. What if GRGs aren't inherently rare, but simply hidden? This shift in thinking has upended the way astronomers interpret radio data. Traditional radio surveys, like those conducted with the Very Large Array, VLA, in the late 20th century, were biased toward bright, compact sources, especially those emitting strongly at higher frequencies, such as 1.4 GHz. These instruments were excellent at detecting radio cores, jets, and fresh lobes, but not so much at uncovering the aged, diffuse remnants of ancient giants. The sensitivity of these surveys dropped off sharply at low surface brightness and at large angular scales, meaning that many GRGs were simply invisible to earlier generations of radio telescopes. The problem wasn't the number of GRGs, it was the limitations of our eyes. Older lobes of radio galaxies, particularly those no longer powered by active jets, undergo synchrotron aging. Their high-energy electrons lose energy quickly, and the spectrum of the radiation they emit becomes steep, meaning the emission shifts toward low radio frequencies. By the time these lobes have aged for tens or hundreds of millions of years, they shine almost exclusively at frequencies below 200 MHz, far below what many surveys were built to detect. Moreover, these lobes can be vast, spanning more than 10 arc-minutes across the sky, and sometimes more than a degree, causing them to be resolved out by instruments not tuned for large-scale, diffuse structures. This means that for every GRG discovered in older surveys, many more may have gone undetected, hiding in plain sight but beneath the sensitivity thresholds. Even when they were present in data, they were sometimes dismissed as noise, overlooked due to their lack of a visible core, or misunderstood because their lobes appeared disconnected or incomplete. In some cases, only one lobe was visible, or the galaxy had moved on, making it hard to associate the structure with any host galaxy at all. Enter the new generation of radio telescopes, LOFAR, MWA, UGMRT Meerkat, and soon, the Square Kilometer Array, SKA. These instruments are designed to observe the sky at much lower frequencies, with higher sensitivity, and with baselines optimized to detect large angular structures. In other words, they are tuned precisely for the kinds of signals that faded, ancient, or fossil GRGs emit. And with them, the number of known GRGs has begun to explode. For example, LOFAR's deep surveys have uncovered dozens of new GRGs, some with lobes over 5 megaparsecs in size, more than 16 million light-years across. These giants had escaped detection not because they weren't there, but because we had not yet developed the tools to perceive them. What's even more remarkable is that many of these newly discovered GRGs lack active cores. They appear as fossils, quiet and cold, yet stretching across incomprehensible distances. It is now believed that many more of these relics may be lurking in low-density environments, waiting to be discovered by instruments sensitive enough to register their faint, ghost-like glow. And this realization opens up new questions. How many GRGs are lurking in the cosmic web, too faint for detection? What percentage of galaxies once underwent massive outflows that have since faded from view? Are we underestimating the prevalence of past AGN activity simply because we've only been looking with high-frequency eyes? Some astronomers now propose that the true GRG population could be an order of magnitude larger than current catalogs suggest. If we include faint fossil lobes, off-axis relict emissions, or asymmetric, single-lobe giants, the number grows. Moreover, even the classification of giant may evolve. As we detect more galaxies with diffuse, extended radio emissions well beyond the traditional threshold of 0.7 megaparsecs, we may need to redefine the boundaries between large giant and ultra-giant. There's also the issue of sky coverage. Many existing deep radio surveys cover only narrow slices of the sky, just a few degrees across. The full sky coverage at low frequencies remains incomplete, meaning that vast swaths of the sky have not yet been examined with the tools capable of exposing these hidden giants. As these surveys grow, such as with the LOFAR 2-meter sky survey, LOTSS, or the planned all-sky maps from the SKA, we expect not just incremental growth in GRG discoveries, but a surge, revealing perhaps thousands or tens of thousands of new examples. Adding to the challenge is the difficulty of identifying the host galaxy for these large, diffuse structures. Many hidden GRGs are now just disconnected lobes with no clear origin. Without a core or visible jets, it becomes a detective game, matching the geometry of lobes to faint optical or infrared galaxies, analyzing polarization vectors, and even tracing environmental alignment. Some of the most massive GRGs found in recent years were only identified after careful visual inspection of radio maps combined with multi-wavelength data, an effort requiring both human insight and machine learning. Indeed, artificial intelligence and automated pattern recognition are now playing a growing role in uncovering GRGs. Algorithms can be trained to detect subtle patterns in noise, spot symmetry between lobe structures, and suggest candidate host galaxies even when the signal is weak or fragmented. This computational approach may be key to uncovering the faintest, oldest, and most ghost-like giants, buried in terabytes of data. In the end, the shift in understanding is profound. GRGs may not be the rare beasts we once imagined. They may be the cosmic elephants hiding in the mist, massive and majestic, but concealed by the fog of our observational limitations. With better tools, deeper maps, and wider eyes, we are now just beginning to perceive the true scale of these radio-emitting leviathans. They are not few, they are forgotten. Not absent, but invisible, until now. Though invisible to human eyes, radio waves carry more than just the presence of a galaxy. They carry structure, direction, and history. One of the most powerful tools in decoding that hidden information is polarization. When astronomers observe radio emissions from giant radio galaxies, they don't just measure the intensity of the signal. They examine how those waves are aligned, or oriented, across the sky, revealing the invisible fingerprints of magnetic fields, particle motion, and past activity encoded in the light itself. Radio waves, like all forms of electromagnetic radiation, can oscillate in various directions. But when those waves are emitted by charged particles spiraling through magnetic fields, as in the case of synchrotron radiation, the dominant process in radio galaxies, the resulting radio light becomes polarized. That is, the electric field vectors of the waves point in specific, organized directions rather than randomly. The pattern of that alignment tells astronomers about the geometry and strength of magnetic fields in the regions where the light was produced. In GRGs, the polarized emission acts as a cosmic compass, pointing the way to how the relativistic jets were formed, how they interacted with their environment, and how they evolved over time. The direction of polarization vectors can trace the magnetic field lines inside the lobes, often revealing large-scale order, even across millions of light-years. In some GRGs, the magnetic fields within the lobes remain remarkably coherent, implying that the jets delivered their energy in a consistent, collimated way over extremely long timescales. But the story becomes even more detailed when polarization is used in tandem with another phenomenon, Faraday rotation. As polarized radio waves travel through space, they can pass through regions of ionized gas threaded by magnetic fields. When this happens, the plane of polarization rotates, an effect proportional to the strength of the magnetic field and the density of the ionized gas. By measuring how much the polarization angle changes with frequency, astronomers can derive what's called the rotation measure (RM). This provides a map of how much magnetized plasma the radio waves have passed through, offering indirect insights into the intergalactic and interstellar medium surrounding the radio galaxy. GRGs are particularly valuable in this context because their massive lobes stretch across vast regions of space, sampling the conditions of the intergalactic medium as they go. Differences in rotation measure across a lobe, or between the two lobes, can tell astronomers whether the galaxy is embedded in a magnetized environment, how uniform that environment is, and whether one jet is traveling through denser material than the other. In this way, polarization doesn't just illuminate the internal structure of a GRG, it becomes a probe of the surrounding universe, turning each lobe into a radio flashlight shining through cosmic fog. Another intriguing clue polarization reveals is jet orientation and bending. In many GRGs, the jets are not perfectly straight. They may curve subtly or dramatically, depending on their environment or the motion of the host galaxy. Polarization vectors can trace these curves, helping astronomers understand jet stability, precession, or even whether a restart event has occurred. If a newly launched jet carves a different path than its predecessor, the resulting polarized emission will highlight those differences, creating a layered, complex magnetic landscape. Additionally, Polarized light can help distinguish between lobes and background noise in sensitive low-frequency surveys. As telescopes like LOFAR detect fainter and older radio lobes, polarization offers a way to validate whether a faint structure is truly part of a coherent radio galaxy. Fossil lobes, for example, may still exhibit polarization even after their brightness fades, especially in the outer regions where the magnetic fields remain stretched and ordered by the last pulses of jet activity. This means polarization can uncover remnants of activity long after a galaxy has gone dark, acting like a ghostly outline of the energy that once surged through space. In some particularly detailed observations, astronomers have even used polarization to identify shock fronts in radio lobes. Where jets collide with the intergalactic medium or expand into denser regions, the plasma can compress, aligning magnetic fields in specific directions and amplifying the polarized signal. These regions show up as bright, highly polarized hotspots, markers of where kinetic energy was converted into radiation and structure, providing insight into the dynamics of jet propagation. Polarization studies also reveal asymmetries in GRGs. One lobe may appear more polarized than the other, either due to differences in the surrounding medium or intrinsic differences in jet power. These asymmetries can suggest a tilted spin axis, an uneven accretion history, or environmental imbalance, helping astronomers reconstruct the forces that shaped the galaxy over time. And beyond individual galaxies, polarization maps across the sky contribute to a broader picture of cosmic magnetism. GRGs, due to their size and strength, serve as beacons in this cosmic tapestry. By comparing polarization across many radio galaxies, astronomers can piece together the large-scale magnetic structure of the universe itself, including the filaments of the cosmic web and the halos of galaxy clusters. In this way, each GRG is not just an isolated event, it's a data point in the universe's magnetic history. In short, polarization transforms GRGs from mere luminous anomalies into diagnostic tools, their polarized light offering a detailed, multidimensional record of the invisible forces that shape them. What looks like faint radiation in the radio sky becomes a deeply encoded message, revealing not only the structure of the galaxy that sent it, but also the history of the space it traveled through. The radio sky, once silent and vague, becomes alive with direction, motion, and memory, thanks to the unique language of polarized light. Giant radio galaxies are not just impressive displays of astrophysical might. They are time capsules, relics that preserve the violent, energetic history of galaxies across hundreds of millions of years. Just as archaeologists uncover layers of ancient civilizations buried beneath modern cities, astronomers study GRGs to excavate the past activity of galaxies, to peer into eras long gone, and to reconstruct the energetic epochs of the universe that no longer shine in visible light. Unlike stars or optical nebulae, which change rapidly and fade from sight, the radio lobes of GRGs endure. Once the central black hole has expelled its jets and gone silent, the colossal lobes of relativistic plasma it inflated do not simply disappear. Instead, they linger, gradually fading but retaining their shape, energy structure, and magnetic configuration for tens or even hundreds of millions of years. These fading lobes become fossils, silent witnesses to cataclysmic events that once roared with unimaginable force. This endurance turns GRGs into a kind of cosmic geological record. Their radial lobes stretch across vast intergalactic spaces, and every wrinkle, every hotspot, every spectral steepening within them tells a story. Astronomers read these structures the way geologists study sedimentary layers or planetary scientists examine the craters of a barren moon. The shape and symmetry of the lobes reveal how steady or chaotic the black hole's activity was. Sharp bends or distortions hint at intergalactic winds or collisions. Regions of aged, low-frequency emission indicate how long it has been since the jets last flowed. Some GRGs exhibit clear signs of multiple eruptions, where newer lobes are superimposed on older, fainter ones, indicating that the central black hole reactivated after a dormant phase. Others have complex lobe morphologies that suggest precession of the jet axis, perhaps due to the black hole wobbling after a galactic merger. These details offer glimpses not just into the behavior of black holes, but also into the merger history of galaxies, the structure of intergalactic space, and the long-term interplay between galactic centers and their cosmic environments. Even the spectral index of the lobes serves as a dating mechanism. As relativistic electrons emit synchrotron radiation, they lose energy, especially the higher energy particles, which fade fastest. By measuring how the brightness of the lobes drops off with radio frequency, astronomers can estimate the age of the plasma. Steep spectra typically point to ancient outbursts, long since ended. This kind of spectral aging allows astronomers to date the epochs of AGN activity, sometimes pinpointing outbursts that occurred before the Earth formed. Moreover, GRGs preserve clues about the early universe. Some of the most distant known GRGs lie billions of light years away, meaning we see them as they existed billions of years ago. These ancient giants provide rare evidence that massive black hole activity, and jet launching, was already well underway when the universe was young. Their discovery challenges models that predict slower black hole growth in early epochs and forces scientists to rethink how quickly galaxies and AGNs evolved. The size of a GRG itself acts as a chronometer. Given that radio lobes expand at speeds of thousands of kilometers per second, their current size can be used to estimate how long the jets were active, how long the lobes have been inflating, and how long they've been fading. A 5 megaparsec GRG didn't form overnight. It's the culmination of hundreds of millions of years of outflow, pushing against intergalactic gas, shaping the medium as it grows. In this way, GRGs are long-form stories, their length and luminosity spelling out the chapters of galactic evolution. Some GRGs are so old and faded that they barely register in even the most sensitive surveys. These ultra-steep spectrum sources and relic radio lobes are like the oldest archaeological ruins, barely visible, nearly eroded, but profoundly important. They hint at the possibility that many galaxies underwent massive radio outbursts in the past and are now silent and unrecognizable, their luminous days long behind them. Finding these ancient remnants requires low-frequency, wide-field telescopes and often the painstaking work of matching diffuse radio signals with faint host galaxies buried in infrared or optical surveys. And just as archaeological ruins reveal cultural, technological, or environmental shifts in human history, GRGs also reflect changes in the cosmic landscape. Their jets may curve or terminate depending on the density of the intergalactic medium. Their lobes may expand differently depending on the surrounding magnetic fields. The symmetry or asymmetry of their structures can tell us whether the black hole had a steady supply of fuel, or whether it sputtered through cosmic droughts and flares. Even polarization angles preserved in the lobes encode information about the magnetic environment billions of years ago, letting us reconstruct conditions that no longer exist. This makes GRGs not just active objects of study, but fossil records of cosmic dynamics. Through them, astronomers can trace the evolution of galaxy formation, black hole growth, large-scale structure, and intergalactic physics. They are the Rosetta Stones of radio astronomy, unlocking ancient scripts written not in stone, but in electrons, plasma, and magnetic fields. And just as the ruins of forgotten cities lie buried beneath layers of earth, many GRGs lie hidden beneath observational noise, waiting for discovery. As our tools improve and our sky maps grow more detailed, we are uncovering more of these giants, and thus more of the universe's past. In this way, giant radio galaxies are not just celestial structures. They are archives, silent and enormous, preserving the legacy of black holes that once carved the cosmos with fire and light. Studying them is like sifting through the bones of creation, tracing echoes, piecing together eruptions, and reading the long-forgotten history of galaxies that once roared. Among the universe's most dazzling phenomena are quasars, quasi-stellar radio sources, so named because when they were first discovered, they looked like stars in optical telescopes, but emitted enormous amounts of radio waves. These are not stars at all, of course. They are the intensely luminous centers of galaxies powered by actively feeding supermassive black holes, outshining their entire host galaxies by factors of hundreds, or even thousands. But not all quasars are created equal. Some shine not only in visible and ultraviolet light, but also in radio waves, with colossal lobes of plasma extending millions of light years from the core. These are the rare and awe-inspiring giant radio quasars, or GRGs. In many ways, GRQs are the cosmic equivalents of combining a lighthouse with a jet engine. They blend the blazing optical and X-ray brilliance of a quasar, powered by a hot, fast-rotating accretion disk, with the monumental, slow-burning radio lobes that are typical of giant radio galaxies. What results is an object that commands attention across the entire electromagnetic spectrum, reaching from the innermost region around the event horizon all the way to radio lobes that can touch the edges of intergalactic space. Quasars are already extreme. They are among the brightest objects in the universe, capable of being seen across billions of light years. In some cases, the light we observe today was emitted when the universe was less than a quarter of its current age. Their power comes from the accretion of matter into a supermassive black hole, where gravitational energy is converted into radiation with dazzling efficiency. A single quasar can emit thousands of times more energy than an entire galaxy of stars. Now imagine such a quasar also launching relativistic jets from its poles, accelerating particles to nearly the speed of light. If these jets continue for long enough and encounter an intergalactic environment permissive to expansion, they can inflate enormous radio lobes, just as in GRGs. When the source at the center of this twin structure is not a quiet galaxy, but a quasar, the system is designated a giant radio quasar. These systems are rare but crucial, as they represent the fusion of extreme luminosity and extreme scale. One well-known example of a GRQ is J1432+158, a quasar with a radio lobe structure stretching over 1.35 megaparsecs, or roughly 4.4 million light-years. Another is B1243+036, a source showing a bright optical quasar core at the center of huge radio lobes spanning nearly 2 megaparsecs. These examples demonstrate that quasar activity can persist long enough, and stay stable enough, to produce truly enormous outflows. What makes GRQs particularly intriguing is that their bright central cores provide extra observational leverage. Because quasars are so luminous across optical, UV, and X-ray wavelengths, they allow astronomers to study the properties of their black holes and accretion disks in much greater detail than is typically possible with a radio galaxy. Spectroscopic studies can reveal black hole mass, accretion rate, spin, and even chemical abundances in the inner disk. When this information is paired with radio observations of the extended lobes, it enables a multi-scale analysis of the same object, from sub-parsec accretion phenomena to megaparsec-scale radio structures. This also allows for the study of how quasar winds and jets coexist. Quasars can drive powerful winds perpendicular to the accretion disk, capable of blowing away gas from the central regions of galaxies. When jets are launched alongside these winds, they may compete or interact. The radio lobes provide evidence of how long-term jet activity manages to push through these outflows and expand over cosmic distances. The presence of large-scale lobes in quasars also challenges older assumptions. It was once thought that radio loudness in quasars was rare and perhaps transitory. But the discovery of GRQs suggests that in some cases, jet activity and radiative quasar activity can persist together for extended periods. This coexistence implies a sustained inflow of fuel and a stable configuration of magnetic fields around the black hole, a balance that is difficult to achieve and may explain why GRQs are so uncommon. Orientation also plays a key role. Because quasars are often detected via their bright optical cores, many of the ones we observe are likely oriented such that the accretion disk faces us, meaning the jets may be angled away from our line of sight. In some cases, this orientation leads to relativistic Doppler boosting, where the jet pointed toward us appears dramatically brighter. These are the blazars, the beamed cousins of radio quasars. But in the case of GRQs, the jets are often not aligned with our line of sight, allowing the lobes to be seen fully extended on the sky, tracing the true physical size of the outflows. Interestingly, GRQs may also be used as cosmic distance markers, since both their optical and radio emissions are visible across vast stretches of the universe. Their powerful optical cores can be used to pinpoint redshift, while their radio lobes provide information about the intergalactic medium through which they've expanded. This makes them valuable tools for probing the early universe, including the state of the intergalactic medium during the epoch of reionization, or the behavior of large-scale magnetic fields. As telescopes like LOFAR, the SKA, and next-generation X-ray observatories continue to come online, the number of known GRGs is expected to rise. Each new discovery offers a chance to study co-evolving black hole accretion and jet production across the most extreme luminosities and scales nature allows. They blur the line between quasars and GRGs, unifying them into a broader class of objects where the brightest cores give birth to the biggest structures. Ultimately, giant radio quasars represent one of the most astonishing expressions of cosmic energy, a single black hole, not only lighting up the sky across the electromagnetic spectrum, but sculpting space itself on intergalactic scales. They are the cosmic fusion of light and force, of brilliance and brawn, and they remind us that even the most concentrated, radiant points in the sky may also cast the longest shadows. Though they stretch across millions of light years, giant radio galaxies are ultimately powered by something unimaginably small by comparison, a supermassive black hole, compressed into a region smaller than our solar system. The fact that such tiny engines can inflate lobes the size of galaxy clusters is among the most extraordinary truths in astrophysics. But the relationship isn't one way. Just as black holes shape GRGs, so too do the structures of GRGs reveal hidden truths about their central black holes. Their size, symmetry, jet alignment, and luminosity form a cosmic paper trail, allowing astronomers to infer properties of black holes we cannot observe directly: spin, mass, and feeding behavior over cosmic time. One of the most significant revelations comes from examining jet power and morphology. The twin jets that inflate GRG lobes are not just arbitrary outflows. They are highly collimated, relativistic beams launched along the black hole's rotational poles. Their power and stability, sustained over tens of millions of years, imply a highly organized system at the core. The consistency in direction and length of these jets suggests that the black hole's spin axis has remained stable for a very long time. This, in turn, hints at either a very massive black hole, whose angular momentum resists perturbation, or a supply of infalling matter that is consistently aligned, perhaps funneled by a well-organized accretion disk or large-scale galactic structure. Spin is especially important. While black holes are defined by just a few parameters, mass, charge, and spin, it's spin that most directly affects jet formation. The leading theoretical framework for powerful jet production is the Blandford-Snejek mechanism, which proposes that magnetic field lines threading the rotating event horizon of a spinning black hole can extract rotational energy and launch jets. The faster the spin, the more energy can be extracted. Therefore, a GRG with particularly large, powerful, or long-lived jets likely hosted a rapidly spinning black hole, capable of sustaining immense outflows over a prolonged period. In fact, simulations show that the spin of a black hole can determine not just the energy of the jets, but also their collimation and persistence. A slowly rotating black hole may produce only weak, short-lived jets that fizzle out before reaching intergalactic distances. A fast-spinning black hole, on the other hand, can drive jets that remain stable for hundreds of millions of years, gradually inflating the enormous lobes that define a GRG. By reverse engineering the observed lobe size and energy, astronomers can estimate the spin parameter of the black hole, even though the black hole itself is completely invisible. Another key property is black hole mass. Supermassive black holes at the centers of GRGs often tip the scales at hundreds of millions or even billions of solar masses. This is inferred partly through their AGN luminosity. Brighter accretion disks generally imply more massive engines, and partly through the mechanical energy required to power the lobes. Larger, more massive black holes can sustain higher accretion rates without exceeding the Eddington limit, the theoretical maximum luminosity at which radiation pressure balances gravitational infall. In some GRGs, the lobe energy suggests a total mechanical output equivalent to the energy produced by hundreds of millions of supernovae, implying enormous central engines. But perhaps the most nuanced information comes from how black holes feed. The structure of GRGs can tell us whether the accretion was steady or chaotic, whether it occurred in bursts or cycles, and even whether the feeding black holes switched on and off over time. For example, a GRG with multiple lobe pairs, such as a double-double radio galaxy, implies episodic accretion, periods of feeding and jet launching, followed by dormancy, followed by a new phase of activity. In these galaxies, the black hole was likely fed by intermittent infall, possibly due to instabilities in the galactic gas supply or external events like mergers. On the other hand, a GRG with smooth, symmetrical lobes and uninterrupted jets suggests a long-duration, consistent accretion flow, likely fed by a stable inflow of gas from the galaxy's halo or interstellar medium. The direction and curvature of the jets may reveal whether the black hole's spin axis has changed, for instance, due to a merger with another black hole or a misaligned gas disk. Any sudden change in jet direction, such as an X-shaped radio galaxy, may indicate a spin flip caused by such an event, reshaping the path of future outflows. GRGs also reveal clues about the composition of the accreted matter. Jets are shaped by the magnetic fields and plasma in the accretion disk. If the feeding matter is magnetically rich, the resulting jets will be highly collimated and powerful. In contrast, weak or turbulent magnetic fields may result in broader, less focused jets that fail to reach large distances. Thus, the morphology of a GRG, including lobe sharpness, jet width, and hotspot brightness, becomes a proxy for the magneto-hydrodynamic conditions near the black hole, something impossible to observe directly. Furthermore, some GRGs show signs of precession, where the jet axis slowly wobbles over time. This could result from a binary supermassive black hole system, where the gravitational interaction of the two black holes causes the jet axis to swing in a predictable arc. These precessing jets leave behind curved lobes or twisted filamentary structures, which act as historical records of black hole dynamics over tens of millions of years. Even the asymmetry between lobes, where one is brighter or longer than the other, can be informative. While environmental factors certainly play a role, such as density gradients in the intergalactic medium, intrinsic differences in jet power or black hole behavior can also cause such imbalances. These may point to variations in accretion rate or magnetic flux, offering yet another window into the feeding habits of the central engine. All these clues add up. By treating GRGs as forensic evidence, astronomers can work backward from what is seen across millions of light years to reconstruct the story of a black hole that is just a few times the size of the Sun. And in doing so, they learn not only about the black holes themselves, but about the mechanisms of galaxy evolution, the feedback loops that regulate star formation, and the growth history of cosmic structures. A GRG is, in effect, the autograph of a black hole, signed across the sky in plasma and magnetism. Each lobe is a brushstroke, each jet a declaration of force. From their shape and scale, we glimpse the secrets of nature's most extreme engines that bend light, twist space, and shape the destiny of galaxies. Perspective in astronomy isn't just a matter of viewpoint, it can dramatically alter the entire appearance and classification of cosmic structures. When it comes to giant radio galaxies, especially those with powerful jets stretching millions of light years, the angle at which we observe them determines what we actually perceive. A single GRG may appear as a vast double-lobed structure, a compact point source, or something in between, all depending on jet orientation relative to Earth. At the heart of this perspective-altering effect is the concept of relativistic beaming. Jets from active galactic nuclei (AGN), including those that produce GRGs, are not just fast, they are relativistic, meaning they travel at speeds close to the speed of light. When such a jet is pointed almost directly at us, strange things begin to happen. Due to the principles of special relativity, the approaching jet appears brighter, shorter, and more compact than it actually is. Its radiation becomes beamed in our direction, an effect called Doppler boosting. Conversely, the jet pointing away from us becomes deboosted, appearing fainter or even invisible. This is why some radio-loud AGNs, when viewed along the jet axis, appear not as lobe giants but as blazars, compact, star-like objects emitting intense, rapidly variable radiation across the electromagnetic spectrum. In these cases, the actual radio lobes, if they exist, are not easily detectable because of projection effects and their faintness compared to the central core. Thus, some objects that are classified as blazars could, from another angle, be identified as giant radio galaxies. When the jets are inclined perpendicular to our line of sight, however, we see a very different picture. Both jets appear roughly symmetrical, extending outward from the core and inflating giant lobes on either side. This side-on view is ideal for studying GRGs because it reveals the full scale of their structures. The lobes can be measured in terms of angular size, converted into linear distances using redshift, and used to estimate ages, energy output, and environmental interaction. In other words, jet misalignment favors discovery of true giants. But this also introduces a bias. Because projection shortens structures aligned with our line of sight, a large fraction of GRGs may be underrepresented in surveys. A GRG with lobes 5 megaparsecs long viewed at a sharp angle might appear to be only 1 or 2 megaparsecs across in projection, or worse, might masquerade as a compact radio galaxy with no visible lobes at all. In effect, many of the largest radio galaxies may be hidden in plain sight, their lobes lost in the angle, their true size obscured by relativistic illusion. This angular dependence also affects classification. There's a critical threshold of projected linear size, traditionally around 0.7 megaparsecs, that separates normal radio galaxies from GRGs. But if a jet is aligned at, say, 30 degrees to our line of sight, its projected size could be only half its real length. That means many radio galaxies just below the size threshold might, in truth, be giants in disguise. Correcting for this requires statistical modeling and assumptions about jet angle distributions across large samples. Jet orientation also influences observed asymmetries. Even if both jets are launched symmetrically from the black hole, one may appear longer or brighter due to relativistic effects. The approaching jet, moving slightly toward us, experiences boosting, while the receding jet suffers from deboosting. This creates the illusion of unequal lobes, even when the underlying physical structure is symmetric. Without accounting for jet orientation, this could be misinterpreted as environmental asymmetry or intrinsic jet instability. Moreover, the brightness and polarization of jets and lobes are also angle-dependent. Doppler boosting can enhance polarization signals in the approaching jet, skewing estimates of magnetic field alignment and jet structure. Similarly, hotspots, the bright, compact regions where jets terminate in intergalactic space, may appear more or less pronounced depending on angle. In extreme cases, only one hotspot is visible, while the other is lost in the background, again giving a false impression of asymmetry. Understanding jet orientation is crucial not just for classification, but for unraveling the physics of AGNs. Theoretical models predict that jet launching is tied closely to the black hole's spin axis and the orientation of the accretion disk. If we observe many GRGs with similar orientation within a cluster or filament, it might indicate large-scale alignment, a tantalizing suggestion that even on cosmic scales, black hole activity might be influenced by structure formation in the universe. Jet orientation also has implications for multi-wavelength observation. For instance, if we're observing a GRG at a steep angle, its X-ray and optical emissions from the core might be obscured by dust in the host galaxy. But a jet-aligned object, such as a blazar, shines brightly in X-rays and gamma rays, offering a different window into the central engine. Thus, the same physical object, viewed from different angles, can present a completely different spectral fingerprint. Finally, jet orientation provides crucial context when interpreting variability. Jets pointing toward us appear to vary more rapidly, due to time compression effects. This can lead to mistaken conclusions about the energy scale, lifetime, or even stability of the AGN unless the geometry is properly considered. In essence, perspective shapes perception, and nowhere is that more apparent than in the world of giant radio galaxies. Their scale, symmetry, and classification are not fixed properties, but projection-dependent illusions, distorted by relativistic speed and cosmic geometry. To truly understand these giants, astronomers must look beyond what they see, and imagine what lies just a few degrees out of sight. Galactic collisions are among the most transformative events in the universe, violent, sprawling interactions that can trigger starbursts, rip apart stellar populations, and permanently reshape the structure of galaxies. but one of their most profound consequences may lie hidden not in the optical glow of merging galaxies, but in the colossal, ghostly shadows of radio lobes stretching across millions of light years. There is growing evidence that galactic mergers and interactions play a crucial role in triggering the birth of giant radio galaxies, turning previously quiet galaxies into engines of unimaginable scale. The basic premise is straightforward. To power a GRG, you need a central supermassive black hole with access to a sustained, massive inflow of matter. Alone, a galaxy might not have enough cold gas near its center to feed the black hole long enough or vigorously enough to launch the powerful, long-lived jets required to inflate such massive lobes. But in a merger, especially a major merger between two gas-rich galaxies, the dynamical chaos drives torrents of gas toward the center, fueling a sudden, dramatic phase of accretion. This accretion event can trigger an active galactic nucleus, AGN, where the black hole begins to convert gravitational energy into radiation and mechanical outflows. If magnetic fields are aligned properly and the accretion is relatively stable, this activity can give birth to relativistic jets, which, over time, push out into intergalactic space. In favorable conditions, such as a low-density intergalactic medium, these jets can grow for hundreds of millions of years, eventually forming the double-lobed structures that define GRGs. But it's not just about fueling the black hole. Mergers also disrupt angular momentum, sometimes spinning up the central black hole, which may be essential for launching powerful jets via mechanisms like the Blanford-Snejek process. If a smaller galaxy merges with a larger one on a misaligned orbit, the resulting transfer of angular momentum can lead to jet precession, spin realignment, or even the formation of multiple episodes of activity, all signatures that show up in the morphology of many GRGs. Some systems display X-shaped or S-shaped lobes, which suggests that the spin axis of the black hole has changed, likely as a result of a past merger or interaction. There are also observational clues that link GRGs to mergers. Many GRGs, upon close examination in optical and infrared wavelengths, show signs of disturbed morphology. Tidal tails, warped disks, stellar streams, or companion galaxies in close proximity. These are classic indicators of past or ongoing galactic interactions. Some host galaxies of GRGs appear double-nucleated, possibly the remnant cores of two galaxies in the final stages of merging. Others sit at the centers of fossil groups, where they may have consumed most of their neighbors through previous mergers, leaving behind a single dominant elliptical galaxy surrounded by a sparse halo of remnants. One compelling example is the Radio Galaxy 3C236, one of the largest known GRGs. Observations of its host galaxy show features consistent with a past merger, including dust lanes and disrupted stellar populations. The galaxy has also shown evidence of re-triggered AGN activity, which could be the result of renewed gas inflow following a second, minor merger or interaction. This supports the idea that not only can mergers start the process, they can restart it, leading to multiple jet episodes over time. Simulations support this as well. Cosmological models show that galaxy mergers, especially in environments with significant cold gas, are efficient triggers for AGN ignition. The gravitational disturbances from such mergers funnel gas inward, overcoming angular momentum barriers that typically prevent accretion. When that inflow reaches the inner parsecs around the black hole, it can launch outflows powerful enough to impact the surrounding galaxy, or, in rare cases, create radio jets that escape into the intergalactic medium and keep going. Interestingly, not all mergers result in GRGs. Most mergers, even those involving AGNs, result in compact radio galaxies, short-lived jet activity, or chaotic, poorly collimated outflows. What differentiates GRGs seems to be a combination of factors: the mass of the black hole, the duration and orientation of accretion, the structure of the magnetic fields, and crucially, the environment into which the jets are launched. But it's increasingly clear that mergers are often the spark that lights the fire, setting into motion the chain of events that leads to the formation of a GRG. Moreover, mergers can affect the long-term evolution of a GRG even after jet activity has ceased. The movement of the host galaxy relative to its lobes, the gravitational shaping of surrounding dark matter halos, and the distribution of intergalactic gas, all altered by merger dynamics, can influence how radio lobes age, fade, or fragment. Some fossil GRGs show distorted or shifted lobes, suggesting the galaxy has moved significantly since launching its jets, possibly due to a gravitational kick from a black hole merger. In a broader cosmic sense, mergers are part of how galaxies grow and evolve. That some of these growth spurts result in GRGs is not a coincidence. The same forces that build galaxies also feed the monsters at their centers, which then carve signatures of their fury into the sky. So do galactic collisions trigger the birth of GRGs? Not always. But often enough that the largest radio giants we see today likely owe their existence to ancient, tumultuous mergers, events that stirred galaxies, awakened black holes, and unleashed jets that still blaze across the radio sky, millions of years after the galaxies themselves have settled into silence. Giant radio galaxies are often viewed as isolated titans, carving through the cosmic darkness with jets that stretch for millions of light years. But many of these colossal structures do not evolve in solitude. Some grow in crowded neighborhoods, galaxy clusters teeming with galaxies, hot plasma, and dark matter. In these bustling environments, GRGs both influence and are influenced by their surroundings in ways that offer crucial insights into the cosmic ecology of galaxy clusters. Studying these interactions reveals how the environment can nurture or constrain a radio giant's growth, and how the GRG itself can reshape the very space around it. Galaxy clusters are the largest gravitationally bound structures in the universe, hosting hundreds to thousands of galaxies, all embedded in a superheated plasma known as the intracluster medium, ICM. This medium, made of diffuse gas heated to tens of millions of degrees, emits X-rays and stretches over several megaparsecs. It is in this turbulent, high-pressure soup that some GRGs thrive, and often, their growth challenges our assumptions about jet propagation, energy distribution, and AGN feedback. At first glance, it seems counterintuitive that a GRG, which relies on the expansion of jets over vast distances, could survive, let alone grow, within such a dense environment. The ICM exerts pressure that can confine or distort radio lobes, and its inhomogeneities can deflect jets or cause them to fragment. Indeed, many radio galaxies found in clusters are small and bent, their jets sharply curved by ram pressure as the host galaxy moves through the cluster's plasma. These are often classified as wide-angle tail, WAT, or narrow-angle tail, NAT, radio galaxies. But GRGs that manage to form and expand in these conditions demonstrate extraordinary resilience, and possibly, unique environmental alignments that allow them to succeed where others collapse. One reason some GRGs can thrive in clusters is location within the cluster structure. Central dominant galaxies, often the largest ellipticals near the gravitational heart of a cluster, are known to host powerful AGNs. In such locations, the motion of the host galaxy relative to the ICM may be minimal, reducing the bending or truncation of jets. If the central region of the cluster is relatively underdense or contains channels of lower pressure, jets can expand preferentially in those directions, forming elongated lobes that reach megaparsec scales. In such cases, the GRG becomes a central engine not just of its host galaxy, but of the entire cluster's energy balance. In fact, GRGs in clusters often play a central role in a process called radio mode feedback. As their jets plow into the ICM, they inflate cavities or bubbles in the hot gas. These cavities can be detected as X-ray depressions and are filled with relativistic plasma from the AGN. Over time, this mechanical energy heats the intracluster gas, counteracting the radiative cooling that would otherwise lead to runaway star formation in the cluster's core. This feedback regulates the thermal evolution of clusters, suppresses the formation of overly massive galaxies, and maintains the balance between inflow and outflow of energy, all thanks to the jets of radio galaxies, sometimes giant ones. Yet the cluster environment doesn't just passively receive energy from GRGs, it fights back. The shape and morphology of a GRG within a cluster can tell us a great deal about the density, motion, and turbulence of the ICM. Jets that encounter asymmetric pressure will bend. Lobes that expand into denser regions will flatten or become compressed. Some GRGs show highly asymmetrical lobe lengths, where one lobe is much shorter or brighter than the other. While orientation effects play a role, these differences can also be the result of environmental drag. A jet pushing into a denser part of the ICM will decelerate more quickly, deposit its energy closer to the core, and produce a shorter, brighter lobe. Clusters can also reignite or sustain AGN activity by channeling gas toward the center. As galaxies interact and strip material, streams of cool gas can fall inward, providing the fuel needed to reactivate a previously dormant black hole. This is one reason some GRGs within clusters show multiple episodes of activity, with inner and outer lobes that indicate at least two distinct periods of jet launching. The cluster acts as a reservoir and recycler, occasionally resupplying central black holes with the matter needed to restart their cosmic engines. Interactions with nearby galaxies within clusters can also leave visible scars on GRG morphology. A jet may collide with the halo of a neighboring galaxy, producing sharp deflections, kinks, or distorted lobe boundaries. In rare cases, this can lead to jet termination or bifurcation, creating structures that look like wings or fan-shaped outflows. These features not only highlight the complex dance of galaxies within a cluster, but also allow scientists to trace the 3D distribution of matter in the region, effectively using the GRG as a probe to map the unseen structure of the cluster environment. What's more, GRGs in clusters may interact with other AGNs. In some dense regions, multiple radio galaxies can lie in close proximity, and their lobes may overlap, merge, or collide. These interactions create tangled, chaotic radio structures that challenge classification but offer a unique window into multi-source radio dynamics. They can also help astronomers test models of how magnetic fields evolve when different relativistic plasmas meet, something that can't be replicated in any lab. Lastly, clusters provide an ideal testbed for understanding how GRGs shape large-scale cosmic structure. As jets inject energy into the ICM, they may trigger shock waves that travel for hundreds of kiloparsecs. These shocks can accelerate particles, seed magnetic fields, and contribute to cluster-wide radio halos, diffuse radio emissions that stretch across the cluster, often surrounding or overlapping with GRGs. The interplay between GRGs and these halos reveals a feedback loop. GRGs inject energy. That energy stirs up the ICM, and the turbulent ICM in turn modifies future jet behavior. In the end, giant radio galaxies within galaxy clusters are not just growing in spite of their environment, they are co-evolving with it. Their jets sculpt the cluster plasma, while the cluster's structure shapes their growth. It's a dynamic, mutual relationship, a dialogue between galaxy and cluster, between black hole and cosmic web. Rather than isolated titans, these GRGs are key agents of transformation, altering their neighborhoods in ways that echo through millions of light years and millions of years. In studying them, we're not just observing radio structures, we're watching galactic ecosystems in action. The more deeply we peer into the universe, the farther back in time we go. Every photon that reaches our telescopes from distant sources has journeyed across billions of light years, carrying the whisper of ancient epochs when the cosmos was young. Among the most astonishing discoveries in this deep time exploration are giant radio galaxies located at extreme redshifts, radio behemoths that somehow managed to inflate lobes millions of light years wide in the early universe, when galaxies were still assembling and the cosmic web was only beginning to take shape. These distant GRGs represent the outer edge of known giants, and they pose fascinating questions about how such enormous structures could form in such a relatively short time after the Big Bang. Their existence forces us to revise assumptions about black hole growth, intergalactic environments, and the timeline of AGN activity. To detect them is to look across both space and time, revealing echoes of ancient cosmic engineering on truly staggering scales. Some of the farthest known GRGs have been found at redshifts greater than 1, meaning their light has taken over 8 billion years to reach us. Consider, for instance, the radio galaxy J1420-0545, located at a redshift of about 0.3, not the most distant, but once the largest known GRG with a span of over 4.8 megaparsecs, more than 15 million light-years. Its sheer size already suggested that giants could grow quickly, even when the universe was much younger than today. But then, deeper surveys began finding similarly large, or even larger structures at much higher redshifts. One exceptional discovery was TGSS J1530 plus 1049, a GRG detected using the GMRT, Giant Meter Wave Radio Telescope, and the LOFAR, Low Frequency Array, which lies at an estimated redshift of about 1.2. That places it more than 9 billion light-years away, meaning it existed when the universe was less than 5 billion years old. Despite this early cosmic age, its radio lobes extend for over 1.3 megaparsecs, or around 4.2 million light-years, a colossal size for such an early epoch. Its existence suggests that supermassive black holes capable of sustained jet activity had already formed and stabilized long before the peak of galaxy assembly. Another striking example is 4C63.20, a radio source located at redshift Z is almost equal to 3.7, meaning its light comes from a time when the universe was just 1.6 billion years old. Though not definitively classified as a GRG due to observational limitations, it exhibits features consistent with megaparsec-scale radio emission. If confirmed, it would represent one of the earliest known examples of giant radio structures in the cosmos, and a testament to the rapid assembly of black hole jet systems in the early universe. Detecting these distant GRGs is an enormous challenge. Their radio lobes are diffuse, often faint, and can be stretched across large angular distances on the sky, especially at low frequencies. Compounding the difficulty is the cosmological dimming of surface brightness, where extended structures become harder to detect at greater distances. This means that many ancient GRGs are likely hiding just beneath our detection threshold, invisible to previous generations of telescopes. However, with the advent of low-frequency radio surveys like those conducted by LOFAR, GMRT, and MWA, Murchison Wide Field Array, astronomers are beginning to uncover this hidden population. These instruments are especially sensitive to the synchrotron radiation emitted by aging electrons in distant radio lobes, radiation that peaks at lower frequencies due to spectral aging. As the lobes grow older and cooler, their emission shifts downward in frequency, making low-frequency arrays uniquely suited for spotting the giants of the past. What do these distant GRGs tell us? First, they reveal that supermassive black holes, SMBHs, of billions of solar masses were already in place when the universe was only a few billion years old. These SMBHs must have grown extremely rapidly, either by direct collapse, frequent mergers, or highly efficient accretion. Second, they suggest that the conditions in the early intergalactic medium, IGM, may have been more favorable for large-scale jet expansion than previously thought. The lower density of the IGM at high redshifts could have allowed jets to plow outward more freely, encountering less resistance, and thus inflating wider lobes. Moreover, these edge-of-the-universe giants help map the large-scale structure of the cosmos. Because GRGs trace the direction of jets over millions of light-years, they can be used as arrows pointing to cosmic filaments, voids, and overdensities. If a GRG at high redshift is found aligned along a filament, it suggests the presence of primordial structure formation already underway. In this way, GRGs act like cosmic weather vanes, responding to invisible forces of the cosmic web across vast scales and epochs. Their discovery also sharpens our understanding of cosmic feedback mechanisms. If massive radio lobes were already common billions of years ago, then the energy injected into the early IGM by AGN jets may have played a much larger role in heating and shaping the intergalactic environment than previously accounted for. This has implications for galaxy formation models, star formation rates, and the timing of cosmic reionization. Finally, the farthest GRGs remind us of our current observational limits. For every one we've detected, there may be dozens or hundreds more waiting to be revealed as telescopes become more sensitive. Instruments like the Square Kilometre Array, SKA, with its unprecedented resolution and sky coverage, are expected to uncover a deluge of high redshift GRGs, pushing the known edge of these giants ever farther into the past. In truth, we are only beginning to chart the outer frontier of GRGs. Each discovery at higher redshift is like opening a time capsule, a radio message from an ancient black hole, preserved in the stretched and redshifted light of its jets. They are the oldest signatures of black hole activity on intergalactic scales, scribbled across space-time by forces we are only starting to understand. These far-flung giants remind us that the universe, even in its youth, was capable of creating structures of sublime enormity, and that, billions of years later, we can still hear their radio echoes across the cosmic gulf. Could our very own Milky Way, the galaxy we call home, one day unleash twin jets of energy, carving massive lobes into intergalactic space and becoming a giant radio galaxy? The idea may seem far-fetched at first glance, especially given the tranquil state of our galaxy's center today. But when we look closely at the necessary ingredients, and at the deep-time evolution of galaxies across the cosmos, the possibility becomes less science fiction and more a matter of timing, alignment, and cosmic coincidence. At the heart of nearly every GRG lies a supermassive black hole, one capable of launching relativistic jets for millions of years. The Milky Way does, in fact, host such a monster, Sagittarius A, a supermassive black hole with a mass of about 4 million times that of the Sun. While this is on the smaller end of the supermassive black hole spectrum, it's still massive enough to potentially power an AGN phase, provided it receives the right kind of fuel. Right now, Sagittarius A is largely dormant. It's accreting only a trickle of material, emitting weak X-rays and radio waves, and displaying none of the ferocity associated with active galactic nuclei. But that may not be its permanent state. Black holes can awaken when conditions change, when a large cloud of gas falls inward, or when the galaxy undergoes a merger that funnels fresh material to the core. If such an event were to occur, our quiet galactic center could erupt into a brilliant, energetic beacon capable of launching jets that, over time, might stretch far beyond the visible edges of the galaxy. Intriguingly, we may have already witnessed the faint afterglow of such past activity. In 2010, NASA's Fermi Gamma Ray Space Telescope discovered two massive structures rising above and below the Milky Way's plane, the Fermi bubbles. These gamma-ray emitting lobes extend about 25,000 light-years in either direction from the center, suggesting that Sagittarius A experienced an energetic outburst millions of years ago. Though much smaller than the lobes of a GRG, the Fermi bubbles are significant. They're radio-visible, symmetric, and suggestive of past jet activity or AGN-driven winds. Some scientists believe they may be the embryonic traces of radio lobes, arrested early due to insufficient fueling or confined by the surrounding galactic medium. So, what would it take for the Milky Way to evolve into a true GRG? Several factors would need to align. First and foremost is fuel. The black hole at our galaxy's center would need access to a significant influx of matter, especially gas dense enough to form a hot, accretion disk. The most likely source of such a meal would be a galactic merger, the kind of dramatic encounter that funnels gas inward and spins up the black hole. The good news, or bad news, depending on your perspective, is that this is already on the calendar. In about 4.5 billion years, the Milky Way is expected to collide and merge with the Andromeda Galaxy. This merger will be transformative. The two spiral galaxies will eventually coalesce into a giant elliptical, and their central black holes will spiral toward one another and merge into a much more massive core, perhaps tens of millions of solar masses. During this process, huge amounts of gas and dust will be dislodged, driven inward by gravitational torques. If that material reaches the merged black hole's accretion disk, it could ignite a new AGN phase far more powerful than anything seen in the Milky Way today. Under such circumstances, the merged galaxy, sometimes referred to as Milkomeda, could indeed become a GRG. Its newly awakened core might launch twin jets of relativistic plasma, expanding far beyond the galaxy's visible boundaries and eventually forming radio lobes millions of light-years across. If the intergalactic medium around Milkomeda is sufficiently low in density, these jets could expand freely, meeting little resistance and sustaining their growth over hundreds of millions of years. Moreover, simulations show that such AGN outbursts are common following major mergers. Galaxies that were previously quiet often light up in radio, X-ray, and optical wavelengths shortly after a merger, a period known as AGN ignition. The merger with Andromeda might provide not only the fuel but also the realignment of angular momentum and magnetic field structure needed to sustain powerful, collimated jets. If Milcomeda's central black hole ends up spinning rapidly, which depends on the spin alignment and mass ratio of the original black holes, the conditions could be ideal for a Blandford-Snagic mechanism to launch long-lasting jets. Could those jets eventually make Milcomeda a GRG? There's every reason to think so. GRGs are typically found in massive ellipticals, which are the end products of major mergers. They often sit in underdense regions that allow jets to propagate freely. If our future merged galaxy finds itself in such an environment, and the jets remain active for long enough, there's no fundamental reason why the lobes couldn't reach megaparsec scales, placing Milcomeda among the radio giants of the distant future. Of course, this transformation wouldn't happen overnight. From the moment of merger to the peak of AGN activity might take hundreds of millions of years, and the lobes would take another few 100 million years to grow to giant status. It's a long, slow process, one that unfolds over timescales longer than the lifespan of stars and even planetary systems. But in the grand timeline of the universe, it's entirely plausible. And there's one more thought to consider. Even if the Milky Way never becomes a GRG, it may already be surrounded by ancestors of giants. Several nearby galaxies, such as Centaurus A, Hercules A, and Fornax A, are radio bright and show evidence of extended lobes. These may represent various phases of GRG evolution, scattered across our cosmic backyard. So while we may gaze with awe at the titanic radial lobes of Alcyoneus or 3C236, we should also remember that our own galaxy may one day join their ranks. Given the right trigger, the right merger, the right spin, the right flow of matter, our black hole could roar to life, light up the sky with jets of plasma, and leave behind lobes that stretch across intergalactic space. Not in our lifetime, but perhaps in the lifetime of the universe itself. The discovery of giant radio galaxies, those vast, whispering structures spanning millions of light years, has always depended on the technology we use to look into the radio sky. The further we push the limits of detection, resolution, and sensitivity, the more of these cosmic giants emerge from the shadows. For decades, the known population of GRGs remained small, largely because the instruments at our disposal simply couldn't see far or faint enough. But that's changing. With the arrival of next-generation radio telescopes, we are entering a golden age of discovery, an era in which thousands of previously invisible GRGs are expected to be revealed, some stretching beyond our current understanding of galaxy evolution. At the forefront of this revolution is the Low Frequency Array, or LOFAR, a European radio telescope that operates at frequencies between 10 and 240 MHz. Unlike traditional dish-based telescopes, LOFAR is a distributed array, made up of thousands of simple antennas spread across multiple countries. These antennas act in concert to create a synthetic telescope with an enormous effective aperture, capable of high-resolution imaging at very low radio frequencies. LOFAR's strength lies in its ability to detect the faint, extended emission that defines the lobes of aging radio galaxies. These lobes, often composed of ancient, cooling plasma, emit most strongly at low frequencies due to a process called synchrotron aging. As electrons spiral through magnetic fields over millions of years, they lose energy, and their peak radiation shifts downward in frequency. That makes low-frequency instruments like LOFAR uniquely suited to detect the dying embers of ancient GRGs, structures that older, higher-frequency surveys would completely miss. And LOFAR is not just detecting faint sources, it's revealing structures with astonishing resolution. Its wide field of view and deep sky coverage have already led to the discovery of Alcyoneus, the largest known radio galaxy to date, whose lobes stretch over 16 million light-years. Before LOFAR, this source was entirely overlooked. It wasn't that Alcyoneus didn't exist, it was that we lacked the ears to hear its radio voice. The success of LOFAR has led to an explosion in new GRG discoveries. The LOFAR 2-meter sky survey, LOTSS, an ambitious effort to image the entire northern sky at 150 MHz, is uncovering hundreds of GRG candidates, many of which are likely larger or older than anything previously catalogued. These discoveries are reshaping our understanding of how common GRGs truly are, and how limited our previous surveys had been by both frequency and sensitivity. But even LOFAR is just a step towards something far more ambitious, the Square Kilometer Array, or SKA. Slated to become the most powerful radio observatory ever built, the SKA will consist of two major components, SKA emit in South Africa and SKA low in Western Australia. Together, they will cover a frequency range from 50 MHz to 15 GHz, with unprecedented sensitivity, resolution, and survey speed. The SKA's collecting area of 1 square kilometer, as its name suggests, means it will be able to detect radio signals 10 to 50 times fainter than current arrays. That makes it the ideal instrument for probing the deep radio universe, including low brightness, ultra-large GRGs that have so far remained undetected. The SKA will be able to peer into the epoch of reionization, identifying radio-loud AGNs, and potentially GRGs, that formed in the universe's first billion years. These early giants, if they exist in significant numbers, could profoundly impact our models of early black hole growth and intergalactic feedback. In addition, the SKA will allow scientists to study the polarization of radio lobes in exquisite detail, revealing the magnetic field structures within and around GRGs. It will help track how jets interact with the cosmic web, how lobes evolve in different environments, and how radio galaxies grow across billions of years. With its sensitivity and resolution, the SKA is expected to discover tens of thousands of new GRGs, turning what was once a niche class of radio source into a rich population that can be statistically analyzed across cosmic time. Other cutting-edge instruments are also contributing to this surge in GRG detection. The Meerkat Array in South Africa, for example, has already produced some of the most detailed radio images ever taken, including stunning views of the relativistic jets and lobes in several nearby radio galaxies. Meerkat's combination of resolution and sensitivity has made it a key player in transitional discoveries, bridging the gap between older arrays like the Very Large Array, VLA, and the future capabilities of the SKA. Meanwhile, the ESCAP, Australian Square Kilometre Array Pathfinder, is performing rapid, wide-field radio surveys, enabling the detection of rare and unusual sources, including extended radio galaxies that were previously missed due to limited sky coverage. Even space-based missions are on the horizon. Though radio astronomy has traditionally been confined to the ground due to the Earth's atmosphere, future missions may use space interferometers to bypass ionospheric distortion and observe the longest radio wavelengths with high clarity, wavelengths ideal for detecting the ultra-aged lobes of ancient GRGs. As all of these tools come online, they will allow astronomers to ask entirely new questions. How do GRGs evolve over billions of years? What determines their ultimate size? Are they more common in certain cosmic environments or epochs? What role do they play in the heating of intergalactic space? And do they, as some theories suggest, align with large-scale structures like cosmic filaments, pointing to a deeper connection between AGN activity and the fabric of the universe? Each new telescope is like widening the aperture of our ears, allowing us to hear more clearly the long, slow thunder of black holes sculpting the universe. These instruments are not just detectors. They are time machines, reaching back through the epochs to uncover the grandest structures ever formed by galactic activity. As the next generation of observatories begins to survey the radio sky in ways never before possible, the true population of giant radio galaxies, their diversity, their origins, and their legacy, will finally be revealed. The giants were always there, waiting. Now, with sharper tools and deeper vision, we're finally listening. Despite decades of observation, imaging, and theory, giant radio galaxies remain enigmatic. They are among the largest single structures ever observed, jets of matter, energy, and magnetism stretching across millions of light years, powered by invisible engines that defy complete understanding. And though modern radio telescopes are uncovering more of these behemoths than ever before, each new discovery brings with it a fresh batch of puzzles. The truth is, GRGs exist at the very intersection of what we know and what we're still trying to figure out. Their sheer scale poses profound questions, not just about individual galaxies, but about black holes, the universe's structure, and the forces that have shaped cosmic evolution for billions of years. One of the biggest lingering questions is deceptively simple. Why do some radio galaxies become giants, while most remain small? While many galaxies have active nuclei capable of launching jets, only a tiny fraction produce outflows that span megaparsec scales. Are GRGs fundamentally different in terms of black hole properties? Or is their size dictated more by environmental conditions? Or could it be that all radio galaxies start off with the same potential, and only a few are allowed to grow to their full extent? Understanding jet power is at the heart of this mystery. The process by which a supermassive black hole launches twin jets at nearly the speed of light is still not entirely understood. The most widely accepted model is the Blandford-Znajek mechanism, in which energy is extracted from the spin of a black hole via tightly wound magnetic fields. But questions remain. How much spin is required? What determines the duration of jet activity? How do the mass and angular momentum of the accretion disk influence jet collimation? Even among active galaxies, jet strength varies drastically. Some fizzle out after a few 100,000 years, while others burn brightly for hundreds of millions. GRGs seem to fall into the latter category, but we still don't know why their engines are so enduring. Compounding the mystery is the role of the intergalactic environment, a subtle but powerful factor that may place invisible boundaries on growth. As jets travel outward, they must push through the intergalactic medium, IgM, a sparse but widespread web of gas, plasma, and dark matter filaments stretching between galaxies. Though thin, the IgM is not empty. It exerts drag, especially on the older, slowing lobes of GRGs. This resistance, often termed cosmic drag, can sap the momentum of the jets and limit how far they travel. The density, temperature, and structure of the IgM all affect jet expansion, and yet we know surprisingly little about the IgM's detailed properties, especially in the large-scale voids where many GRGs reside. Do GRGs only grow in special pockets of low-density intergalactic space, where jets can expand freely? Or do some of them possess enough intrinsic energy to punch through denser regions as well? Observations of asymmetrical lobes, where one side is longer or brighter, suggest that environment plays a major role, possibly outweighing the intrinsic properties of the AGN itself. But the precise interplay between jet energy and environmental drag remains an open and evolving field of research. Then there's the problem of lobe aging and spectral steepening. As electrons lose energy through synchrotron radiation and inverse Compton scattering, the radio spectrum of the lobes changes, typically becoming steeper at high frequencies. By measuring this change, scientists can estimate the radiative age of a GRG. But these calculations rely on assumptions about the magnetic field strength, electron injection timescales, and energy loss rates that are still fraught with uncertainty. In some cases, different aging models can produce vastly different age estimates, raising doubts about our ability to confidently determine how long these structures have existed. Are we looking at ancient giants from the distant past, or more recent outbursts from unusually powerful AGNs? Another open question involves the intermittency of AGN activity. Observations suggest that many GRGs go through multiple active phases, producing double-double radio galaxies or even triple-lobed structures where past and current jets are visible simultaneously. But what controls these cycles? Is the central black hole being repeatedly refueled by minor mergers, accretion disk instabilities, or gas inflows from the galaxy's halo? And how long are the dormant periods between active outbursts? We still don't know if episodic activity is common or rare, or how it influences the eventual size of the radio structure. Even the definition of a GRG is somewhat unsettled. Traditionally, radio galaxies exceeding 0.7 megaparsecs, about 2.3 million light-years, in total extent are labeled giant. But this is an arbitrary boundary, and as more low-surface brightness giants are discovered, we may need to redefine the threshold. Some of the largest known GRGs, like Alcyoneus, were completely missed by earlier surveys due to their extremely low brightness per unit area. This raises the question, how many more giants are out there, lurking below our detection limits, waiting for next-generation instruments like the Square Kilometer Array to find them? And then there are deeper theoretical challenges. Could the growth of GRGs be influenced by dark matter halo mass or black hole spin alignment with cosmic filaments? Are their jets aligned preferentially with the large-scale structure of the universe, suggesting a connection between GRG orientation and the cosmic web? Some studies hint at weak correlations, but the data remains inconclusive. Finally, one of the most profound questions is whether GRGs are a universal phase in galactic evolution, something every massive galaxy could go through under the right conditions, or whether they are truly rare, exotic events caused by a precise and unlikely combination of factors. If every galaxy with a supermassive black hole has the potential to become a GRG, then these giants are not anomalies, but milestones in galactic life cycles, like stellar supernovae or planetary nebulae. But if their formation depends on a perfect storm of properties, ultra-spinning black holes, low-density environments, sustained accretion, and magnetic field alignments, then GRGs are the cosmic lottery winners, unique signposts of conditions that rarely converge. So many questions. So few answers. And yet, that's the beauty of the giants. Giant radio galaxies sit at the outermost boundaries of what we can observe, model, and understand. They are the megastructures of natural astrophysics, formed not by alien civilizations but by gravity, magnetism, and time. Their unanswered questions are invitations to build better telescopes, to write deeper simulations, and to listen more carefully to the silent roar of black holes across the dark radio sky. Scattered across the cosmic web, these giants whisper across time, their voices silent to the eye, yet roaring in the radio night. There is something haunting in the way giant radio galaxies exist, invisible to our naked eyes, yet more massive and sprawling than any object we can comprehend. They do not flash or glitter or blaze like stars. They do not pull in our gaze with spirals or color like the photogenic galaxies that decorate textbooks. Instead, they hum, long, slow, deep hums in radio wavelengths, echoing through the cosmos like the distant horns of creation itself. To look upon a GRG is to view a shadow of violence turned into structure. Twin beams of plasma, hurled out by black holes that drink too deeply, collide with intergalactic space and blossom into colossal lobes that glow for millions, sometimes billions, of years. And yet, all of this happens beyond our visual spectrum. We walk beneath their presence unknowingly. We look into the sky and see stars, but behind that veil, behind the light, the universe is whispering in radio. Each GRG is a memory etched into space-time, a frozen footprint of a once-raging engine now quiet. These lobes are not just relics, they are stories. Stories of galactic cores that awoke from slumber, spun up magnetic fields, and ignited jets of light-speed particles. Stories of jets piercing the IGM, carving out massive cavities in the darkness. Stories of lobes billowing out like intergalactic clouds, slowly fading over hundreds of millions of years as the cosmic microwave background steals their energy one photon at a time. And yet, even as they fade, they are not lost. We hear them with instruments that were impossible just a century ago. We chart them with arrays that link continents. And in their discovery, we are reminded of the staggering patience of the universe. GRGs do not rush. They do not dazzle for a moment and vanish. They persist. In a cosmos governed by entropy and impermanence, these giants endure, monuments to invisible power, to quiet force, to persistence beyond the scale of stars, planets, and even civilizations. Perhaps that is what makes them so moving. Not just their scale, though that alone stuns. Not just their power, though it humbles. But the fact that they exist in a language we cannot hear, yet now choose to learn. They call not with light, but with radio waves, whispers cast across billions of years, surviving the deaths of stars, the collision of galaxies, the cooling of voids. They are ghosts across the void, and yet in listening to them, we find the universe more alive than ever. In their lobes, we find the echoes of supermassive black holes. In their shape, the scars of collisions and cosmic weather. In their fading edges, the trail of time itself. GRGs are cosmic time-lapse paintings, massive canvases splashed with the aftermath of ancient engines, still glowing faintly across the ages. And as we stand on a tiny rock orbiting a yellow star, wrapped in our fragile layer of atmosphere, we build great ears to listen. We tune in. We hear. Because in the end, to study giant radio galaxies is not merely to understand a class of astrophysical phenomena. It is to eavesdrop on the long conversation of the cosmos, to interpret messages sent before our species existed, messages that tell us we are latecomers to an ancient stage where the actors are galaxies, the dialogue is electromagnetic, and the story is still unfolding. And in this deep radio night, where silence dominates the visible, we learn to see with different eyes, and hear the giants calling through the dark. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.